Okay, let's go ahead and get started. Thanks, everyone. Really appreciate everyone coming to the 30th annual CSM workshop. I'm Dave Lawrence. I'm the Chief Scientist of CSM. Welcome. Really glad to see so many people here in person online. And so we're going to start this morning with a welcome from Everett Joseph, who can't be here because he's at the Board of Trustees meeting in DC. So he's going to kick us off with an opening welcome. So, Everett, sounds good. Thanks. Thanks.
as facilities. At NSF, there's a specific definition for facilities. NWSC, our research aviation programs, our instruments, but I consider models as well as facilities. And we're going to continue to support our facilities, including our models, because we know that these models, these programs, and your ability to access them. Access is important for us at NCAR. It has always been and it continues to be important. Lead to scientific discovery that have far-reaching benefits for society. These models, these programs, further our ability to understand and advance prediction of, for example, extreme events, and to do so at timescales in a way that really matters to decision making. On a lighter note, this is a special year. This workshop marks a remarkable 30 years of CESM. And that is 30 years of innovation and development that has produced one of the most advanced Earth system modeling programs in the world. That is really a powerful tool for science, but not only a powerful tool for science, but really a powerful tool for social benefit, for society and social benefit. It's really 30 years of discoveries that have increased our understanding of the Earth system to the extent that we are better informed on how to make communities more resilient to high impact events, high impact weather. Also as at the benefit to the benefit of our economy and just our overall security as a society. And it's also 30 years of community modeling. This community is really rooted in community modeling, of convening and of building a vibrant international and interdisciplinary community of experts and users. The community that really surrounds CSM, and I've learned to appreciate this in the time that I've been at NCAR, and even before I came to NCAR, the community that surrounds CESM has really been indispensable to its success and scientific achievements. It's also a special meeting because we're also celebrating Warren Washington, NCAR's distinguished scholar, internationally recognized leader in atmospheric and climate science. Warren is a pioneer in Earth system science. He's been dedicated to mentor to countless of students and early career scientists, and is a trailblazer for underrepresented scientists. Warren was a personal friend and certainly a mentor to me. And when I think of him, I think of someone who had a rare combination of what I call grace, wisdom, and courage, and qualities that really enabled him to chart a path for our community, for our science, and for many of us to follow. And it's clear that his legacy lives on in our shared passion for Earth system modeling and for science that really benefits society. He was a real champion for that. There'll be a celebration in Warren's honor tomorrow afternoon, and I'm really sorry I'm missing that. There'll be more information in that, I believe, coming. I also want to thank all the plenary speakers here this week on topics ranging from model development, model assessment, to the development and use of data sets like our large ensembles, like our recent Mesoclip project, to more applied work with far-reaching societal benefits. There are also cross-working group sessions at the workshop this year focused on machine learning, AI, and developing and applying CESM at higher resolution. This is really exciting. This is an evolving direction for us, and really exciting to hear the outcome of those sessions. On the topic of AI machine learning, just a few words on that. I want to share very briefly that The approach we're taking at NCAR is one to scale and apply AI on our work. As you all are aware, the last couple of years, new AI models have proliferated and proven, in many cases, to perform as well or better than our physics-based models, particularly at shorter time scales. These are NWP models, shorter time scale forecasts, and larger scales. Um, these models have achieved this performance using really a tiny fraction of computing resources compared to traditional dynamical and physical models. So at NCAR, when we think of this, we really have a responsibility at NCAR to provide leadership in this space of how we apply AI and machine learning to advance Earth system science, to advance our science. It's really what we do. It's what we're here to do, is to help with the development of innovations and to take those innovations and applying them, be a leader in that space. And to achieve that, we have been doubling down. We've been developing what we call an AI initiative or AI roadmap, which really is an effort for NCAR, again, to provide leadership and capabilities in particular in what we call community AI. And this is, you can think of it conceptually very similar to community modeling and the leadership that we provided in community modeling over the years, which this community is an example of. And our plan is to build an integrated framework of data, of infrastructure, framework of that includes computing resources, software tools, modeling systems, and training. Training is really important, with the goal of enabling researchers across domains, doesn't matter what domain you're in, across domains, to effectively harness AI and machine learning in their work to advance their science. And a particular thing we want to do is we want to ensure the reproducibility. Reproducibility is important, scalability, and broad accessibility. Again, accessibility is what we do at NCAR. We democratize science, we democratize access to resources. And so that's important here. And accessibility of AI models for weather and climate, for the weather and climate community. And at NCAR, we don't think that AI means the death of physical models. Far from it. We think that physical models continue to have an important role to play, obviously, especially in sort of, the time scale that this community works on. And it's really integrating physical models with AI. At CGD has really been a trailblazer in this space, in Earth system modeling of from seasonal to decadal prediction through, for example, like the LEAP project. I mention this because we will absolutely, I talk about AI, talk about all this stuff, because we will absolutely need your input to move forward in this strategy successfully. So we look out for forthcoming communication on this. And then again, there's some sessions this week that will be on in this area. We look forward to the outcome from the sessions this week to really guide how we develop and proceed in this initiative. So I'll wrap up by saying that the development and research that will be shared this week is significant, has always been significant, and I don't expect anything less. And the impact of that work will continue to even be more significant. This workshop really represents a community that is dedicated to furthering national resilience through partnership. So thanks again. Sorry for not being there, but I wish you an insightful and incredibly productive week, as it always is at a CESM workshop. So thanks again. And Dave, thanks for the time. And I'm turning it back over to you, Dave.
Great. Thank you, Everett. Thank you very much for taking the time out of your busy schedule to come give us these nice remarks. And I want to echo Everett's comments about welcoming everyone and really appreciate everyone being here. Here at NCAR, we work really hard with you to build this tool for everyone to use, and it's a reward every year to see the people who are making use of the model and interesting and impactful applications. So it's really fun, and of course this year marks the 30th anniversary, which is again quite remarkable that this activity is going on for 30 really plus years. So I'm going to start off now with the traditional state of the community or system model project talk, and I'm just going to jump right into it. So, this is the 30th year, and what we've achieved over 30 years, we're going to get to discuss over the course of this week. We have a really fun event tomorrow to kind of review some of the early days of CSM, and also to celebrate Warren Washington, and to hear from all the former chief scientists about their perspectives about their time during development of CSM and when they were leading the activity, and also on their perspectives of the future of our system modeling. So just a reminder on codes of conduct: please be respectful, collaborative, consider different opinions, communicate openly, and be mindful of others. This is still true today, as it always is. If there's any issues, please contact either me or Elizabeth, and in particular, if there's any technical issues, also we have this CSM workshop support alias. We have nursing rooms, all gender restrooms, support for anything you need. So please, especially let Elizabeth know if you need anything during the meeting. A few workshop logistics before we really get started. In addition to all the oral science sessions, we have a really exciting program this year. As always, we're going to do a group photo in the Monday afternoon break in the lobby, so right after the session ends. So working group co-chairs try to keep to time this afternoon so we can get that photo done. There's a poster session and reception this evening. There's a faculty network for teaching. I'll talk about a little bit more Tuesday lunchtime meeting. And then there's a celebration tomorrow afternoon, tomorrow night. There's these cross-working group sessions that Everett already mentioned on AI, ML, and high resolutions. And then on Wednesday at the end, we have this summary session. Last year we tried to solicit questions ahead of time. That didn't really work. So this year we're just going to go with having an open session. So be thinking about questions you want to ask of the leadership of CSM during that afternoon wrap-up session. And we have quiet spaces located around if you need to take a break from the 200 plus people who are here. There's places where you can go. And then I want to also really express my thanks to everyone who's made this possible. The National Science Foundation is providing support, especially helping some early career scientists make it to this meeting. And then really this completely would not be possible without the efforts of Elizabeth Faircloth. This meeting in particular is even more complicated than these already complicated meetings with all the celebration activities that we're having planning going on tomorrow night, and then also all the funding situations that we're having to deal with as well at the same time. So she has been working incredibly hard over the last 2 to 3 months to get this in place. And then the CG administrative team is also providing a lot of help, and the UCAR multimedia services. So really I want to express my thanks to everyone, and I'm sure I'll do that again during the meeting. Okay, I'm going to start with essentially addressing, a little bit the elephant in the room, which is the funding situation. And as Everett mentioned, we're anticipating we can really expect cuts to NCAR, and really everyone here is experiencing cuts within their own programs. So one of the things we're trying to do to address this is, better characterize the impact and use of the CSM activity so that we can be arguing with whomever was willing to listen to us about the value of CSM, potentially looking for alternative sources of funding if necessary. So please, you should have received this already in your email last week, and we'll send it out again. But please fill in this survey. We're really looking for hopefully to come out of this with a list of the top 10, 15, 20 most impactful science contributions, and then also use of CSM outside of the academic context, so by private industry, by government, by stakeholders. And here's just an example, a nice example that Alice DeVivia sent to me, about how CSM, the large ensemble, is being used coupled with ecology models, ecosystem models, to inform Antarctic conservation initiatives. So working with NGOs to develop assessments of the vulnerability of ecosystems in the Antarctic region. So a great example of the kind of thing we're looking for as we try to make the case for the utility of CSM. And then another slide here that I got from James Dunn, or adapted from James Dunn, about the reinsurance industry, which likes to use Earth system model app, and particularly CSM and the large ensembles to understand risk out at 1 year, especially timeframes, but even going a little bit longer. And they're really interested in the frequency and intensity of weather events, which are material to their losses, right? Directly material. And they really want to know about outliers, tails, and not the mean. That's where large ensembles really come in to understand it. You can't even really look at the observational record and really get a good understanding of those outliers, the big events, and large ensembles are what you can use that. And especially the CSM1 high resolution ensemble has proven to be quite useful. So these are just a couple of examples of kinds of things we'd like to hear about from you. So please share the survey link with your colleagues, especially colleagues from the private sector, NGOs, government institutions, et cetera, who might be using CSM. And then in the same vein of impact, I think education is a big aspect of CSM that sets us a little bit apart from other Earth system modeling efforts. We really spend a lot of our energy on education and not just teaching people how to use CSM, but really teaching people climate science. And we're going to need climate scientists. We're going to need hundreds, maybe thousands of climate scientists to go out into industry and to help companies and businesses and government institutions understand how to deal with climate change. That isn't going to go away. So we're going to need that. So one of the things we're doing is trying to build this network of faculty to get together to help each other, and us to help them, and them to help each other, to be able to bring CSM into the classroom. We're finding quite a bit of interest in the use of CSM in the classroom, and some faculty are already doing this, and so we want to draw on the experiences of existing faculty. So please come on Tuesday lunchtime to hear more about this, or also just keep your eye on our communication channels. Okay, so I'm gonna start today with the science stuff on CSM3. It's been the thing we've been focused on for the last 2, 3, 4 years, and I wish I was up here saying that we have CSM3 ready. So at the 2024 workshop, we were using the term working towards CSM3, a little bit less committing. I want to get us this week to be talking about finalizing CSM3, really moving the terminology. We're already talking about this. John is really encouraging me to push the group to do this. People are working incredibly hard already, but finalizing, we need to get to CSM3 for lots of different reasons. So what is CSM3 going to look like? This is what I showed last year. This has not changed. So the component models have all been upgraded. We have significant updates to all the component models within CSM. The full list of changes is available at this link, and you'll get these slides afterwards. It's also available on the CSM website. And there's 50 plus changes across all the different modeling components. So it's not easy to characterize the 1 or 2 things that are going to be better. It's improved physics, improved capabilities throughout the system. And you really find the details if you go to the working group sessions throughout the remainder of the week. But, and as I'm sure many of you are aware, that our problem child for the last 20 plus years has come back. We had a period last year when everything was looking good. With the lab sea freeze, it was not freezing. We had a series of like 30 or 40 or 50 test simulations where it wasn't freezing. We were feeling pretty good about ourselves and things were making progress. And then we finally got all the component models to really have their final configuration. We put it together, and then the lab sea freeze came back. So it's like embarrassing that this still exists. I will say that this problem is shared by several other modeling centers around the world. This is not just us. Almost every time you talk about it, people say, oh yeah, we've had that problem or whatever. So anyway, it's been our focus for the last 3 or 4 months. It's making it difficult to assess and resolve other issues, and so I'm going to talk a little bit about strategies we've had to move past this so we can be working on those lab sea freeze while also working on other things. And maybe the most concerning thing here is that in this latest run that froze, it was actually 200 plus years in, which is the longest we'd ever seen into an integration where a lab sea froze. We thought that if we got past about 60 to 70 years, we were safe, and then it froze at 200 years. So this is making us, give us a pause, to say the least. And really, I think what it comes down to fundamentally, I mean, there's a lot of potential issues, but it's most likely, fundamentally, there's just too much fresh water coming into the Labrador Sea region. And this is just an sort of evidence of that. This is the East Greenland, Iceland region off the east coast of Greenland, southeast coast of Greenland, and it's the gray curve there is what the MOM model uses for input from runoff from this region, which is observations in quotes, I guess, but it still is more like observations, and then this is what we're getting in a couple of our simulations. So you can see a pretty strong 30-40% too much water coming in. It really has to be coming from precip at some place upstream. So that seems to be fundamentally the problem. There's issues with mixing potentially also in the ocean and other potential sources, but fundamentally there's too much freshwater flux coming into the region, and that's not easy to fix in a coupled or system model. You can't just tune something to make your precipitation go down. So a few things we're doing. One is we just started this activity where we're getting the CGD machine learning group to start exploring whether we can use AI to understand better the signatures of what's happening, because we're putting our eyes on it, a lot of smart brains on it, but the system is complicated, right? It's hard to figure out what we should be focusing on to understand really what's happening, and so we're curious whether or not we can bring AI into this and see if we can identify some signatures that we can't figure out with our brains. So that's one thing that's happening. We do have some relatively good news, and all this is cautious, is that we have some relatively recent runs that are showing quite promising behavior, where we've turned off this Bodner sub-mesoscale mixing scheme just for the Labrador Sea region, something the oceanographers will maybe hold their nose at, but can live with doing that, and it's looking promising. It doesn't look like it's vulnerable to freezing, but of course it remains to be seen. And we're also testing whether the club explicit diffusion can be turned off, which is maybe better way to treat it. Also reduces evaporation fluxes from the oceans, which may also result in lower precip in the Arctic. So we're testing both of those things, and both of those are showing some promise. So it's not all bad. So that's the thing it's been spending a lot of our time on, but of course that's not the only thing that's going on. We've kind of developed 3 high priority biases that we'd like to address. You could look at an infinite number of things in the model, but these are the 3 things we've been sort of spending our time focusing on. Some issues related to ENSO, and I'll go into a little bit more details on here in a minute, especially the El Nino to La Nina transitions. Amazon and Africa precipitation biases, but can really screw up your land carbon cycle if they're wrong, and then excessive Antarctic sea ice. So these are the things that we're sort of thinking that, if we can resolve this Labrador Sea, we'd like to take a stab at trying to resolve these before we finalize. But we may not be able to resolve all of them. That's possible. So this is the problem with El Nino. This is on the left is showing the El Nino autocorrelation. What you see is the observations there in black, and then there's an autocorrelation timescale of about 12 months the transition, kind of representing the transition from an El Nino to a La Nina state. And we had it pretty good in the CSM2 large ensemble, is essentially matching the observations. That's also shown there on the right with CSM2 looking quite good in terms of the transition from El Nino to La Nina. But CSM3 for reasons that we're sort of getting some insight into, isn't really transitioning properly. And this is an older slide from an older simulation, but the problem is showing up in many of our recent simulations as well. So this is important. It has implications for for understanding variability in the system. It also seems to be projecting onto different aspects of the El Nino as well that seem problematic. So we're working on this one quite a bit as well. And one thing we're doing, with that lab sea freeze, it was kind of preventing us for a while from making any progress at all. But then we realized that we could apply this strategy in the ocean that's called salinity restoring in the Labrador Sea region, just the Labrador Sea region, its capability of MOM6, that's enabling us to kind of let the model keep running for long time periods, hundreds of years that you need to evaluate the ENSO problem without freezing. And so that's kind of a nice feature that we realized maybe a little bit later than we wanted to, but nonetheless we're using that now to be able to run longer simulations while we're dealing with trying to resolve the Labrador Sea freeze. We're also trying to set off a set of CSM3 initialized predictions, starting off with focusing on the 97, 98 El Nino, and seeing if we can learn something from having an ensemble of real world El Ninos and see what the transition looks like in that system, and see if it helps us understand things and get to an understanding of what's going on quicker than what we can have with century scale simulation. So that's another strategy that we've just adopted recently, and hopefully we'll have results on that soon. Another bias that we're trying to deal with is the Amazon and Africa precipitation biases. So up there on the upper left, this is the JJA dry season in the Amazon, at least, period, and it's really, really dry. There's almost no precipitation in the Amazon, and this really kills off our vegetation, leads to pretty warm temperatures. Kind of combination of the high temperatures and the low precipitation tends to kill off the vegetation. It appears to be coupled maybe with a excessive precipitation in the Sahel or the tropical Africa. And Isla Simpson identified, there's a divergence pattern that looks like it's related. What's interesting here is that it only shows up in coupled simulations, or it's much worse in coupled simulations than it is in CAM, AMIP simulations, which does indicate that it's a coupled problem. Maybe it's SST biases in the tropical Atlantic, possibly the tropical Pacific, that are leading to this. So we're seeing some of this in some recent simulations. We're also showing some promise here. And then the other one we've been working on is the Antarctic sea ice is far too extensive, and especially in the winter, in the Antarctic winter. And so what you see there, the greens, the OBS, and the couple of recent simulations are showing quite a bit too much ice. 5 million square kilometers too much ice. And it looks like it's related to maybe some zonal wind, but it's also a coupled problem. It tends to show up, it's much worse in coupled situations, and maybe some combination of the position of the jet along with ocean mixing. So again, something we're trying to explore as a team to try to figure out. So just want to highlight here, we're doing all this as open as possible. So if you're interested at all in tracking or helping out with any of our issues, we have this sort of new process of tracking our bugs and our biases and our simulations in our open CSM dev repository. So these links will be available. These are all hyperlinks here that you can go to, and it's kind of a nice way to see what we're tackling. And if you have any insight, we always are appreciative of hearing any new ideas about how to tackle these problems. But that's not all bad. Some things are looking good too. So other features of the CSM beta simulations, and there's been more analysis in the working group sessions coming up. But one of the things is the global temperature trend. So some of our first simulations, we were a little bit concerned that the temperature trend didn't look right, but it's actually, I think, looking pretty good right now, although it's been a while since we've been able to run a full transient simulation due to lab sea freeze. But this is the observational based estimates at Ensemble called the Descent data set, which is a 200-member ensemble accounting for the uncertainty and observations. And this is what the CSM2 large ensemble looked like. So it looked pretty good. We had that kind of excessive or too rapid warming towards the end of the 20th century due to this issue with biomass burning, aerosols, not smooth biomass burning. Overall looked pretty good. And here was one of the recent CSM simulations. We also haven't done the smoothing, so it does have an acceleration towards the end, which we think will go away once we do the smooth biomass burning. But looking okay, it's within the realm. If we try to break it down over land and ocean separately, these are the time series from the descent observations. What you see is that actually, if you look at separating out between land and ocean, over land, CSM2 wasn't really warming enough over much of the 20th century. It was relatively small warming occurring until pretty late. If you look at the CSM3 beta simulation, it actually looks pretty good, probably potentially even better than the CSM2 simulation looked. And on the ocean side, it looks about the same, pretty good in both simulations. So there's some promise that CSM 3 is looking better in terms of the temperature trends, and maybe it's due to aerosol radiative forcing. Actually, quite a bit weaker estimates of the aerosol radiative forcing in CSM3 at about minus 0.5 compared to minus 1.65 in CSM2. Although that was assessed before we had the new dust emissions, so it has to be revisited. We're also keeping a close eye on the Greenland surface mass balance, and the first simulations that we were looking at were looking pretty bad in terms of the mass balance. So if you look at the red lines here on the right, that's precipitation average over Greenland. Those are from a CSM3 test case. The black line is a quasi-observed data set from this high-resolution model called RACMO, and then the range in the light blue or purple is coming from the CSM2 large ensemble, which we had a decent looking surface mass balance in CSM2. So in the CSM3 test simulations, it was looking pretty bad actually. There was way too much precipitation in the Arctic and way too much melt. The melt was really bad. So looking through it, we really need this reasonable surface mass balance if we want to run interactive ice sheets. So as in CSM2, we adopted this strategy to artificial enhanced subgrid orography along the really sharp gradient coastlines in Greenland, and that reduces the excessive precipitation. So that's the one thing we did. We sort of adopted the same strategy that worked. And then excessive melting seemed to come through a change we made in the snow conductivity scheme, reverted back to the older scheme just over ice sheets, and we're using this new Sturm scheme over land, which is showing good features over the land in terms of the snow densities there. So looks like we've got what looks like is going to be a reasonable surface mass balance. We've been running a few tests now with a fully coupled MT. That's the mid-top configuration that resolves the stratosphere, which is going to be our core default workhorse simulation. And the QBO amplitude is looking good, especially good agreement below 30 hectopascals there on the right. The black is in the observations, and the blue is this coupled test case, so it's looking pretty good. The QBO amplitude looks about right if you look on the figures there in the middle, but the period's a bit too fast, and the westerlies are phases maybe too strong. So we're trying to see whether or not there's some tuning knobs we can do to help make that better. The oceanography group, or ocean model working group, is looking at to see whether or not to turn on the kinetic energy backscatter parameterization, which they've been testing with, and it has some really nice features. These things called the so-called Tsuchiya jets. I don't know how to pronounce it or even really what it means, but not being an oceanographer, but that's these jets here that are occurring at depth in the equatorial region, which were not occurring in POP, and were not occurring in the default MOM6, and are occurring when you turn on this energy backscatter. And so these have some nice features, including better treatment of the oxygen minimum zones, which is, I think, going to lead to better ocean biogeochemistry. So the oceanography group is hoping that this will continue to show good results, good impacts. And then lastly, I just want to kind of return to this issue that we talked about last year, which is trying to address this issue of the high ECS and microphysics in CSM2, and this question of whether or not CSM2 is usable for climate change projection science over the 21st century. And so Margaret Duffy led and submitted a paper with a lot of help from Isla and Christina McCluskey and others, a really nice paper that's now in review at James. We've got their first reviews back, and the key points we learned from that is that CSM2's climate sensitivity is too high, and the simulations are too cold in the ice age climate. So it's raised questions about its skill. But what we're finding is that the changes to the microphysics representation can improve its ice age climate, and it doesn't appear to impact the transient climate response. And that's what you can see on the right there, where both the original and the resolved improved simulations with match the observed ice age are essentially lying on top of each other in terms of the transient climate response, and also within the large ensemble. So we believe that CSM2 is appropriate for studies of historical climate and 21st century warming. There may be cases where you may want to be careful, especially in extreme climates, and we outline that in this paper. And I'll just make one point. We have been testing in CSM3, and CSM3 beta simulations are showing a good ECS of about a lower ECS of about 3.8 degrees Celsius, and it's also passing the LGM test. So that's good news. Hopefully that holds all the way through the end. And then as we finalize the science configuration and resolve issues, it's a slide I showed last year, but it's the same is true here. We're going to continue, and we are evaluating this broad set of metrics, but we just got to keep in mind CSM2 was and is a really good model. It was matching a lot of observational targets, and so whether or not we're going to be able to beat CSM2 remains a little bit up in the air. We had some things we know are not as good, and some things that are looking better. So we're going to find out about that. But I think it's okay if we don't beat CSM2. That's okay. I think that we're going to have better physics, we're going to have more faith in our model, even if it's not necessarily beating in terms of statistical sense. So really quickly, I want to just go through a few tools and just note that we're working on tools to make your lives all better. We're working on ingesting the CMIP7 forcings, allowing us to make projections out, or historical simulations out to present day. We've got a team working on that. We're testing in the CSM2 Wacom to make sure it doesn't give us some really crazily different results when we move to CSM3. We're trying to do a better job of tracking what we've done as well. So really appreciate especially the team in ACOM here, the chemistry group, who's spending a lot of time working on that. We're working on all our workflows. So a lot of the workflow stuff broke between CSM2 and CSM3 as we moved to machines, as everything moved up to Python. We're redoing everything and trying to make it in a more sustainable way and also more usable by the research community so that you can use all these workflow tools in your own science and make everything easier. I'm not going to go through the details here. We're trying to embed most of it, a lot of it, within this CSM Unified Post-Processing and Diagnostics package called Cupid. So just be aware that we're working hard to make your lives easier, I think, is the main point here. Hopefully we get successful. And on the Cupid side, I don't want to spend too much time on this, so I have time to talk about other things, but we're making a lot of progress on this package to really help you do your science and really enable you to run all the diagnostics that we're used to running here on your own machines. And here's just an example of where you can call at runtime within Cupid and ask for, say, the land model, the ILAM package, which is the land model benchmarking package that we've developed with DOE. You can now call that straight out of Cupid. You don't have to know anything about the package. It just does everything for you. And we're doing as many of these sort of externally developed and internally developed packages all in one place to make it much easier. And you can set it up all at runtime if you want. Okay, and the last thing, we've released this visual case gen in terms of tools. It's a really nice tool that allows you to interactively build a CSM case. It sort of controls what you can and can't turn on. It allows you to, abstract some of the things that you don't really need to know and just focus in on the things you're trying to ask. So it's a really nice tool developed by Alper Atunis and colleagues. Okay, so I just want to have a little bit of word on CSM3 release timing. I'm hesitant to go too far here. I have a scratch in my head here. And we're dealing with a situation with budget cuts and things like that. So that's going to be impacting how we can deliver things. But nonetheless, we really need to finish CSM3 for many reasons. That's to enable new science, to set a new baseline for other activities like CSM MLE, which I'll talk about in a minute, and high resolution configurations and other MIPS. So the CSM working group co-chairs, the SOC and the CAB are going to work towards a plan this week to finalize CSM3. It's going to include some more firm deadlines. I think we're getting to a point where we can do that with some of our more promising recent simulations and really just have to accept that we're not going to be able to resolve all our biases. I'd also like to, while we're finishing this end product here, I want us to be thinking about how to resolve what I'm calling the final mile, or Leo Donner said it's not a mile, it's miles, of the coupled development problem, which is really taking us, it's taken us several years now, again, to try to build a coupled model, even after we have essentially the component models essentially ready. And so one thing, that arose last time is that from CSM2 development, it's a couple early and often. It hasn't really solved all our problems, right? We've tried a couple early and often. We came across the same problems that we had last time. So we thought it was going to help. I wouldn't say that it's actually helped us move faster. So maybe we need new strategies. Maybe emphasize, bring AI ML into this coupled model problem, maybe initialize predictions, et cetera. So just again, we're going to be thinking about that. Okay, and move on to some other CSM activities. I gave this slide last year about the forces that are driving our system model development. I'm not going to read through it all, but it's need for detailed information on what climate change is going to be and how it's going to impact people. Earth system prediction, focus on Earth system prediction across different timescales, high resolution configurations going from standard high resolution all the way up to kilometer scale, machine learning, and all the things that it's doing and totally disrupting the way we're thinking about things, changing computing architectures and the need for getting things to the global south. So in terms of this, we have this big ensemble now of CSM high resolution simulations, which you've been hearing about for several years now. We're really excited about this. It's really impactful set of simulations. You'll hear more about that throughout the course of this week. These simulations, really useful. And so we really need to produce a CSM3 version, we think. We skipped the CSM2, we ran out of time. We need a CSM3 version of the high resolution, and we're starting to do some work here. So this is some work done by Julio and Ben Stevens and Cecile and Colin Zarzicki to look at a CSM high resolution configuration in CAM7 simulations and just comparing the cyclone tracks from observed in CAM5 compared to CAM7. And what we're seeing is action is shifted towards the west and south with respect to what it was in CAM5. It looks like the recurvature is better, and there's some indication that this is going to be better, result in better impact and landfall statistics. Remains to be seen. The tropical cyclone count was too high in this first set of simulations, although Julio is saying that with some more recent simulations with some different parameter settings, it's looking better. And we're also using this variable resolution configuration to really reduce the cost of these simulations, especially when we're doing these test evaluations and exploring the other sensitivities. So things are looking actually pretty good, even though this isn't the main focus yet. And we're trying to lay the groundwork so we can move quickly towards a CSM3 configuration once we're done with high resolution configuration once we're done. We continue to work on kilometer scale capabilities. It's a joint effort between CSEG, SEMA, earthworks, storm speed, and 3 different labs at least, CGD, CISL, and M cubed. And it's really a cross-lab, cross-institution activity for sure, and we're going to need to continue to rely on help from the community to make this happen. We have been able to start running some diamond simulations. We are behind the game here in terms of what some other modeling centers can do, but we're catching up, I think. And so we've run some Diamond 1 simulations. We're running some Diamond 2 simulations now too, the winter case, and actually uncovered a snow depth bug that's sort of strangely occurring there, but it looks like we've resolved it. And we're putting an allocation to run a long timescale 1-year simulation soon. So huge thanks to Brian Dobbins, Adam Harrington, and many others across the Earthworks, SEMA, and Storm Speed projects to make this happen. It's been a big effort. We resolved a lot of issues over the course of this effort, and now we have, I think, the basis of a capability which we can move forward with. And this is just one example of what you can do. Adam was looking at some simulations and seeing the first try, when you had just the club shallow convection turned on, the other convection was resolved. It looked very patchy. The deep convection looked very patchy, the image there on the upper right. And when you move to the second simulation where he turned on the club plus the multi-flux plumes, seeing much better looking convection, more realistic spectrum of clouds, improves the transitional cumulus regimes with less patchy work. So, just some indication that with maybe relatively small changes, we can get a better simulation. So thanks to all of them for that work. In terms of Earth system predictability, a priority of NCAR definitely is going to be, I think, a priority going forward, even in a reduced budget situation. We have a couple things to highlight here. A new seasonal prediction hindcast that we've run with a high vertical resolution, where we replaced the CSM2 vertical resolution with CSM3's vertical resolution, but still running in CSM2, done a set of initialized hindcasts, and showing with that new higher vertical resolution quite a bit better skill sort of in the upper troposphere, lower stratosphere, which is kind of interesting to see that improvement there. We're trying to understand this. This land is expected to be a key source of predictability at subseasonal to seasonal timescales, but CSM2 is not really showing that peak in the hypothesized and sort of proven in some cases predictability at weeks 1 to 3 or 4. We're not showing that in CSM2, so we're kind of working to understand why that is. And Meg is leading a team that's working on that. There's going to be a workshop next week about this. We're already finding that maybe if you start to do conditional analysis when you're sort of more in extreme conditions, that there is some predictability even in the CSM system. And then finally, in terms of the new things we're working on, there's working towards this machine learning enhanced version of CSM, CSM3 MLE, we're calling it, which is basically taking Earth observations or high fidelity simulations and using them to develop new machine learning based parameterizations that we can replace specific parameterizations within CSM to more rapidly advance our Earth system modeling capabilities, and also drawing on machine learning based parameter optimization methods to use those observations to make a better model. And so we're making a lot of progress here on both the land and the atmosphere side. We have machine learning estimation tools in place that we're using at least partially in development of CSM3, and we'll fully exploit them for the CSM3 MLE. So thanks to the teams that have been working on that, and you can hear more about this at the machine learning session on Wednesday. In terms of ML-based parameterizations, we have a bunch of candidate parameterizations that are in development across the LEAP and M-squared lines projects that we're considering for inclusion in this MLE, CSM3 MLE. And so just putting the list here, it's spanning all the different components. These are all candidate parameterizations at the moment, but some of these hopefully we'll be able to make it into an MLE. And we've also built in this ability to couple PyTorch or all the machine learning tools, AI tools you have within the Python ecosystem into CSM through FTorch. And so making it easier for the community to do this stuff. And we've also got a team focused together to really try to make this happen, an integration team. Okay, and then just want to conclude for the last few minutes here about a few science highlights. Just try to demonstrate again the scope and the breadth of the CSM activity. I've talked a lot about sort of the core activity of the CSM3 development, but really CSM encompasses so much more than that. And here's just one great example of a high-resolution Whack-A-Mech simulations where they've taken a look at the Hurricane Helene for this quarter degree NE 120 configuration of the WAC-MX. That's really a really expensive simulation as far as I understand. But they're able to show that you can produce hurricane-induced gravity waves that reach the upper atmosphere at approximately 400 kilometers elevation, and the sort of concentric circles you're seeing up in the upper troposphere in the WAC-MX simulation. Winds, that's total electron content on the top, and then the simulated vertical wind on the bottom there. And it's matching up with what you see in the NASA observation. So that's a pretty cool feature. And these gravity waves are generating these small-scale perturbations in the ionosphere, which can impact communications and navigation signals. So this has a real-world impact. The chemistry working group and the ACOM group here have built and are working with a CSM chemistry forecast system to understand, do initialized predictions of atmospheric chemical constituents. And here's just an example showing carbon monoxide from a fire in Canadian fires from earlier this year, or earlier this month, sorry, just a few days ago. Those big fires were happening in Canada. And so this is a cool feature that's being used fairly broadly by different groups around the world, and they're working on, they have a built-in CSM2, and they're planning to move up to CSM3 and moving to Musica and Musica version 1 to enable like regionally defined capabilities and really get detailed information in particular regions. Another cool application is this CSM applications for mountain glaciers. I think it's the first ESM to include dynamic simulations of mountain glaciers, and we can now use CSM and CTSM for regional glacial hydrological assessments. And on the right here is showing the committed loss for these glaciers in the Bernese Alps. If there's no further climate change, we see dramatic committed losses for the glaciers. So this is another cool capability. And then here's a sort of impact-oriented example. This is work done by Iris de Vries, who is at ETH, I think now at Harvard, if I'm right, looking at whether CSM can simulate record-shattering events. So in this case, an extreme precipitation event, one-day extreme precipitation event. And what you see there on the bottom is observations. We had this really massive event, a shattering record that occurred in 2020 or 2021, I guess. And so can you get those in CSM large ensemble? And what you see didn't have any of those really over the historical record, but then there is a really shattering event that's occurring out, in this case, out in 2070. So really, many standard of deviations away from the norm, and so that's indicating an interesting feature. And if you look at the sort of spatial pattern of the atmospheric dynamics for that event, you see it matches up quite well with what actually happened in 2021, although it's happening out in 2071. So that's just an interesting kind of result. And what she's also finding is that the impacts on the probability of a shattering event, record-shattering event, is as likely due to changes in variability as it is to changes in the mean. And what you see there, this is showing the amplitude of the changes in variability. So in the changes in the mean, the probability ratio on the top, and on the bottom, the same thing, probability ratio due to the variability. And so you're actually seeing greater strength coming from the changes in variability than changes in the mean. And then lastly, I just want to highlight this novel emissions-driven CSM 2.1.5 configuration that Peter Lawrence has put together. This set of simulations is our first effort to run emissions-driven simulations for a wide range of ensembles with interactive CO2, but also interactive fire aerosol emissions and interactive BVOCs, and also this new feature in the ocean, coccolithors, which allows you to force the feisty fish model. So a really cool configuration. These simulations are available, to really ask questions about what is the potential impact of interactive CO2, interactive fires under low and high emission scenarios. So that's it. I want to stop there. And I'm not sure I'm going to take questions. I think we ran a little bit over with Everett, and I'm right on time here. So let's just stop there. And I'm not going to take questions because this is also a hard one for people to ask questions of. I've realized that, and also because I want to make sure to give time to our Distinguished Achievement and Graduate Student Award winners, because we really want to recognize them. Please keep your questions and bring them to me personally, or bring them at the end of the week on Wednesday. Yeah, so okay, I'm going to move on then to our Distinguished Achievement Award. So I'm very excited to actually, oh yeah, well, I had a slide here, but I guess we've already moved on. So I'm excited to announce that Dr. Ping Chang from the Texas A&M University has been selected as a recipient of the 2025 CSM Distinguished Achievement Award in recognition of his exceptional leadership in advancing the high-resolution Earth system modeling with CSM. Dr. Chang led groundbreaking efforts to develop and apply CSM's high-resolution capabilities, particularly through the creation of the International Laboratory for High-Resolution Earth System Prediction, IHESP, now known as the MESA-CLIP project. His work has resulted in the largest ever comprehensive suite of global climate simulations capable of resolving tropical cyclones and ocean mesoscale eddies. The MESA-CLIP simulations are transforming climate research, enabling novel insights into extreme weather events, climate predictability at seasonal indicators, timescales, and long-term climate projections. His work has helped establish CSM as a leader in high-resolution modeling with profound national and international impacts across research, policy, and other stakeholder realms. So please join me in congratulating Dr. Ping Chang on this well-deserved honor.
Thank you. Thank you so much. Can you hear me?
Yeah, we can hear you. So unfortunately, Ping could not be here in person. He had a previously scheduled trip to, I think, the ECMWF. In the UK, so he's going to give his presentation here remotely. So thank you, Ping. Appreciate all your work, and go ahead and take it away.
Thank you so much, Dave. Good morning, everyone, and greetings from UK Met Office. Actually, I mean the UK Met Office, not ECMWF. But anyway, the first thing I want to say is that how truly surprised and deeply humbled I'm to receive this news that the recipient of the CESM Distinguished Award. I really apologize for not to be able to join you in person, and particularly in this particular 30th anniversary of CESM events. I really hope that you have a great and successful workshop. And second, I want to emphasize that this award is just not for me. Really, it's not for me. It really belongs to the entire project team. And from the very beginning, and this has been a collaborative effort. As many of you know, Dave mentioned already, the project actually began as an international partnership in 2019 and under the IHESP initiative. And it's later evolved into a US-funded MESA-CLIP and IPOX project. So this recognition reflects the dedication and the hard work of every team member. So as you can see from my slides, there are a long list of the names here. So unfortunately, I don't have the time to individually acknowledge all the individual contribution, but I want to thank everybody, and really, I feel incredibly fortunate to work with such a committed and a talented team, and to advance high-resolution climate modeling, and to make a meaningful contribution to the CESM community. So thank you again for the tremendous honor, and I think it really meant a great deal to me and to our entire team. So with that, I'd like to just spend a few minutes to highlight some of the key accomplishments we've made over the past 6 years and using the high-resolution CESM. So next slide, please. So first, let me quickly just introduce to you what the high-resolution CESM is. So for those of you don't know this already, and the high-resolution version we're running is actually based on an early version of the CESM 1.3, and as described by Mio et al. 2019. And this model was really derived from earlier high-resolution CESM 1.1 version and described by Small et al. In 2014. And the reason we choose this older version of the CESM for primarily two reasons. One is the computational cost, because we knew this project is going to demand a lot of computational resources. And we realized that the CSM2 is actually computationally a lot more expensive than the CSM1. And the other main reason is that there's no readily available high-resolution configuration of the CSM2. But on the other hand, the CSM1 already have a high resolution configurations before they tested. So that's the reason why we went with the older version of the CSM1. So in terms of the model configuration, we have atmosphere CAM 3.5. We use the SE die core with a 1/4 degree horizontal resolution and 30 vertical level, and the same resolution for the land surface model, CRM 4.0. And for the ocean, we use the 1/10 degree or 10 kilometer horizontal resolution and with 32 vertical level. And we turn off the Jan McWilliam mesoscale 80 parameterization. We also turn off the sub-mesoscale parameterization and overflow parameterization. And then the CIS model is the same resolution as the ocean. And for the coupler, we did backport to the CESM2. And we have ported code to multiple HPC system, including Fontera at University Supercomputer Center TAC, and also Derancho at NCAR. So just give you a sense of the computational speed on 223 CPU processors on the nodes at Derancho, and we can run this version of the model 5 simulation years per day, and with the with high frequency output. So that's very efficient. And finally, I just want to mention the cost ratio between the high res and the low res is about 100. So you run 1 year high resolution model, you can run 100 years of low resolution model. So far we have accomplished many sets of simulations. And so on the right side of the panel, this slide, you can see all the simulation has been mostly completed. So the first we completed the high resolution MIP ensemble. And then the majority of the time we spend is actually completing this CMIP DAC simulation, which consists of 650 years pre-industrial control simulation and 3 10-member ensemble simulations, including the historical ensemble, RCP 8.5 and 6.0. And we also performed a single member simulation of RCP 4.5 and 2.6. And then we complete the 2 climate sensitivity simulations, the 1% CO2, the transient climate sensitivity, and the quadruple CO2 equilibrium climate sensitivity simulation. And so far we completed the 4-member ensemble of AMIP simulation. So that's the entire DAC set we've been working on for the past few years. And then in addition to that, we're also still working on the high resolution decadal prediction a set of simulation, and the results is already published in 2023 by Steve Yeager et al. So in addition to that, since we're using the IC die core, and so we also run as comparable corresponding low resolution sets of simulation, so we can do a apple-to-apple comparison between the high resolution and low resolution. So if you're counting all the simulations I've done so far, so cumulatively we have integrated the model for 6,000 years, and we generated about 7 petabytes of data, so very large data. And finally, I want to emphasize that the data has already been published, and not all the data, but lots of data. Most of the 10-member ensemble data has been published already, and the PI control simulation has been published already. So if you go to our project website down below here, you can actually get access to all the data. Next slide, please. So in the next few minutes, I just want to show you highlight some of the key difference between the high resolution and the low resolution, and to see what the new features we actually can learn from the high resolution model. So this slide just compared the global mean temperature simulated in the high resolution ensembles and the low resolution ensemble. So the red and the orange lines are showing the high resolution simulated the global mean temperature, and the blue and the gray-blue kind of color line showing the low-resolution model. So you can see the high-resolution model agrees much better with the observation. The observation is showing in these shorter lines here. So the red is showing the SST, and the orange is showing the surface air temperature. And the black here is showing the GISTEMP 4.0, the version 4 global mean temperature. And you can see the high resolution model actually very nicely simulates the observation. The low resolution, on the other hand, has a obvious cold bias and by about 1.5 degree or so. Next slide, so. So not only so in general, the high resolution model is actually warmer than the low resolution, but that's not all the case. So if you look the eastern boundary upwelling zones, the high resolution model is actually produce a colder upwelling zones. So in this panel, you can show you can see the comparison of the observed CESM temperature along the eastern boundary current region. So in California, Canaria, Peru, Chile, and Benguela region. The top panel is showing the observation. The middle is showing the high resolution model, and the simulation. The bottom is showing the low resolution model. So you can see the high resolution model is able to capture this narrow cooling tongues along the coast. So it's very nicely simulates the upwelling, the ocean upwelling system, much better than the low resolution model. So this could mean that the high resolution model can have more credibility to projecting to project the future ecosystem changes, and potentially important for the future fishery planning and so on. Next slide, please. So the other interesting thing is that if you look the climate sensitivity, so this is the transient climate sensitivity comparisons. It turns out that the high resolution model and the low resolution model has very similar climate sensitivity, and the difference is about 10%. The high resolution model is slightly higher. But on the other hand, if you plot the temperature difference between the high resolution and the low res as a function of location, and then you can see there's some really large differences. Particularly the high resolution model, the climate sensitivity is much higher in the Arctic region, implying that the high resolution model actually has a stronger Arctic amplification. But on the other hand, the high resolution model also showing a much lower climate sensitivity in the southern ocean, in the southern hemisphere. And so that's also very interesting. And so we had a paper published last year and showing that one of the reasons the high resolution model have a stronger Arctic amplification is through the Bering Strait ocean heat transport. So it turns out that in the high resolution model, the model resolved the Bering Strait transport is much better than the low resolution model. And in high resolution model, there are a lot more ocean heat transport from the Pacific into the Arctic Ocean, which causes a rapid sea ice melting and give you a much faster warming in the Arctic region. So that's very interesting results. So next slide, please. So that relates to the Southern Ocean. The low sensitivity in the Southern Ocean is also reflected to some extent in the cooling trend simulation of the model. So here I'm showing you the trend of the SSTs over the last 4 decades, from 1980 to 2022, and the top panel is showing the observation. So the ERSST, the SST cooling trends you can see in the Southern Ocean and in the tropical South Pacific, and then that corresponds to sea level pressure trends. See this very strong, the pressure gradients in the southern hemisphere, and then the trends in the westerly winds in the Southern Ocean. And if you look at the low resolution model in the bottom, and the low resolution model shows almost no trend at all. in SST, no cooling trends in SST. Everywhere you look is the warming trends. And the sea level pressure trends and the wind, westerly wind trend is also much weaker compared to the observation. But if you look the high resolution model simulation, now we start to seeing the cooling trends in both the Southern Ocean and in the South Tropical Pacific. And we also see a much stronger the trends in the sea level pressure and winds. So next slide. So if you plot the ensemble spread, compare the ensemble of those low res and high resolution model here, choosing two boxes. One is in the South Tropical Pacific, and the other one is the zonal average of the Southern Ocean, showing the bottom here. And you see this, the blue dots represents the ensemble spread of the high resolution model. And the low resolution model from the same model, right, is showing in the green. We did a 10-member ensemble of the same model at 1 degree resolution. And then the purple dots showing the large ensemble, CESM large ensemble. So you can see none of the low resolution ensemble capture any of the cooling trend. None of the ensemble member actually is able to simulate the cooling trends. And but the high resolution model, at least 3 of the high resolution ensemble actually showing the cooling trends, right? So the red line here is showing the observation. So you can see that the observation is the ensemble spread of the high resolution seem to be able to encompass the observation nicely. So next slide. So this improvements in the Southern Ocean cooling trends also translate to the improvements of the decadal prediction scale. And this is the paper published by Steve Younger in 2023. Steve essentially shows that if you compare the anomaly correlation coefficients of the high resolution decadal prediction and the low resolution decadal prediction, and look in the difference, which is showing on the right panel, upper right panel here, you see that the Southern Ocean is showing a much greater improvements. And the bottom panel here just showing the time series averaged in these boxes here. And you can see the top panel or the top row here is showing the low resolution, and the bottom row here is showing the high resolution. And you can see that the low resolution in many of these regions showing this spurious warming trends, where the high resolution model does not have this the warming trends, unrelated warming trends, and therefore give you a better scale in prediction. And in this paper, and Steve also argues that the high resolution model actually increased the signal to noise ratio significantly compared to the low resolution model. So next slide, please. So finally, I just want to show you some of the results for the extreme precipitation, and this is still work in progress. So what we show is that the high resolution model is capable of simulating extreme precipitation much better than the low resolution model. Here we're comparing the extreme precipitation trends in the the extreme precipitation, not the trend, the total extreme precipitation measured by the annual maximum daily precipitation using the Hadley-centered data. And in the middle, showing the high-resolution 10-member ensemble, and the right is showing the low-resolution 10-member ensemble. And you can see the high-resolution model reproduce the amplitude of the extreme precipitation much better. Right? And in the bottom panel, we're showing the difference between the high-resolution and the low-resolution simulation, showing the panel A here. And the panel B is showing the contribution from the resolved precipitation. And panel C in the bottom is showing the contribution from parameterized contribution. And you can see almost all the contribution in the high-resolution model, improvements in the high-resolution model, is coming from the resolved component. In fact, the parameterized component is actually doing the opposite. Next, please. So it turns out one of the reasons the high-resolution model is actually better simulating the extreme precipitation is its ability to simulating mesoscale convective systems. So this is the result using the MOAP tracking algorithm developed by Andrea Prey. And so we save the hourly output of the high resolution model, and then apply this tracker, the MOAP tracker, to the simulated data, and then compare to the observation. And so the top left is showing the observation. This is MCS occurrence frequency measured by days per year. And the middle is showing the high resolution model results. And the right panel is showing the low resolution model. As you can see, the low resolution model, notice the color scale has changed, reduced by a factor of 50. So the low resolution model essentially does not have any MCSs, right? And the bottom panel is showing the phenomenon most frequently occur during the extreme precipitation. And you can see in many parts of the world, the MCSs is really accompanied with the extreme precipitation. And this orange color indicates the MCSs. So you can see that the high resolution model is able to capture this feature very nicely. And the low resolution model essentially has no MCSs. So most of the extreme precipitation in the low resolution model are accompanied by jets and fronts. So it's a very different physical phenomenon, or the mechanism. Next slide, please. So finally, because we are able, the high resolution model is able to simulate extreme precipitation and MCSs better. So we can look in the future projection and look at the comparison of the low resolution model projection and the high resolution model projection. And you can see that the increase in the extreme precipitation projected by the high resolution model is significantly higher than the low resolution model. And one of the reasons for the much higher increase in the extreme precipitation, the high resolution model, is really due to the changes in the MCSs. So it turns out that under the future warm climate, we'll actually see a shift in the PDFs of the MCSs. So there's going to be more stronger MCSs, more the number of stronger MCSs occurring in the future. So the low resolution model missing these features altogether, and we speculate that's one of the reasons why the low resolution model projects a much lower increase in the extreme precipitation. So next slide, please. So just a few takeaways, and we have developed the first high resolution CMIP DAC ensemble and released that to the public. So we have done a long pre-industrial simulation, historical and future scenario simulation, as well as the decadal prediction simulations. And we found that the high resolution model offers substantial benefits. It reduces the climate biases, and it improves the prediction scale and signal to noise ratio, and is able to produce a more accurate simulation of extreme precipitation. And so we believe the high resolution model is a more reliable tool for the future projection, climate projection and prediction. So the other thing I want to point out is that even though at this resolution the model is not resolving convection and mesoscale, sub-mesoscale ocean features, but the high resolution model is able to improve the simulation of many of the mesoscale phenomenon, such as MCSs and the mesoscale ocean eddies, and the interaction between the ocean atmosphere and mesoscale. And finally, I want to point out that I think these advances open the new frontiers for research and technology in the future, including machine learning, machine learning-based model, and some of the novel diagnostics for understanding explicit and parameterized physics in climate modeling. So with that, I end, and be happy to answer any questions. Thank you.
Thank you, Ping. Excellent presentation. Do we have any questions for Ping? We can take one or two. Yep.
Thank you. Thanks for a nice talk. So I was just interested in asking you about the Southern Ocean sea surface temperature. Specifically, have you seen what we say, the signal to noise ratio in sea surface temperature in the Southern Ocean? Because I've seen there was a bit of a warm patch near the Antarctic Peninsula. So would really like to ask you about that. Thanks.
Yes, I think Steve has looked into the signal to noise ratios in detail. I think Steve is probably attending the workshop. Perhaps you can talk to Steve in more detail and to learn his analysis. And in his paper in 2023, he showed a metric and showing the enhanced signal to noise ratio. I'm not sure if the signal noise ratio is particularly analyzed for the Southern Ocean, but overall there is an increased signal to noise ratio in a high resolution model compared to the low resolution model.
Thank you so much. Thanks.
Great. Another question or? Okay. Yeah, Isla.
Also had a question about the Southern Ocean temperature trends. I hadn't really appreciated how much more variable the high res was, and it seems like maybe almost there's some members that look like the low res and then another set of members that are doing something different. Have you looked into why there's so much more variability?
Yeah, I mean that's absolutely true. There's quite a bit of ensemble spread, and but some of the ensemble member. I think one of the ensemble members looks very, very similar to the observations if you look at the spatial structure, and others are very different. So, yeah, I mean, this is definitely a problem we're still working on. And but in the end, I still think it's the cooling trend is primarily a forced response, and it's not internal. But we're still working on that.
Great. Yeah, one more.
Looking at the improvements in the eastern boundary upwelling and the improvements in the subtropical highs and subpolar lows, it seems like I'm just wondering if there's any relationship between that, if there's some feedback on where that cold zone in the ocean is, and if that's feeding back to improvements in those trends in the subtropical highs. Thanks.
Yeah, that's a great question. I mean, the upwelling, the improvements of upwelling, we wrote a paper about that. We think it's really related to the improvements in the coastal winds. The high resolution model actually gets a much better coastal, not only the strength of the winds, but also the structure of the winds, which actually contributing to the wind stress curl along the coast. So it turns out that curl, I think Justin Small had some paper examine this question, that it turns out that wind stress curl is actually very important to drive the upwelling. So one of the reasons is that. Now, in terms of the sea level pressure, I do believe there's an inference of the improved SST on the sea level pressure pattern. Yeah, but we have not looked into in very details for this problem.
Thanks.
All right, thank you, Ping. Appreciate it. Great talk, and obviously a lot of motivation for why we're moving towards trying to build a CSM3 high resolution. We need a photo. We have your award. You're going to have to come get it. Just kidding.
When I get a chance, I
want
will.
to get a photo with you as well with it next time you're in Boulder. But so let's thank Ping again for his congratulating.
Thank you so much.
And then last in this morning session, I want to announce the Graduate Student Award winners. In this case, it's two. So we had a statistical tie for the awards, and we had this ranked choice voting. I decided I didn't want to deal with that. I just want to recognize two different people who did great work. So it's a better way to do it anyway. So our two winners this year are sitting near the front here. Giovanni Sejo Ellis, stand up. And Jonas Shaw. So they're each going to give a short presentation. So Giovanni is going to go first. We do have awards here, which I'll hand out to them. You guys are going to get this. We'll get a photo after, okay? Okay, so Giovanni has been selected in recognition of his pioneering contributions to regional ocean modeling within CSM. As a PhD student at University of Colorado, Giovanni led the development and implementation of the regional CSM MOM6 component model, introducing a completely new capability to CSM. His work not only advanced our understanding of salinity variability in the Caribbean Sea, but also created essential workflows and documentation that now support downscaling CSM simulations to high resolutions of 1 to 10 kilometers. Though Giovanni is now a faculty member at the University of Puerto Rico at Mayagüez, he remains a valuable collaborator in CSM and MOM6 regional modeling efforts. We congratulate him on this well-deserved award.
Thank you, everyone. Thanks for having me here. I'm deeply honored to receive this award, particularly on the 30th CSM workshop, a great milestone. My name is Giovanni Seijo-Ellis. I'm currently an assistant professor at the University of Puerto Rico, Mayagüez, but not that long ago at all, I was a PhD student at CU Boulder. And today I'm gonna, in a very short and concise way, try to take you to a little bit of the history, my history as a scientist, as a graduate student, and some of the research that I did in collaboration with NCAR and CSM. And I want to start by a very short story. I started my graduate studies in 2017. I moved out of Puerto Rico in the summer of 2017, and 2 months later, if I can advance, there we go. Okay. 2 months later, Hurricane Maria devastated the Caribbean region. In particular, Puerto Rico, U.S. Virgin Islands, the Dominican Republic, and many of the other nations. And it was a very overwhelming time. I was away from my family, couldn't do much about it, but also knowing that extreme events like hurricanes were likely to become more frequent, and just feeling that maybe we haven't done enough. And that sort of set the stage in some ways for a lot of the work that I've been dedicating my graduate studies and I would like to dedicate my career to. Extreme events are only, next slide, please. Oops, there we go. Extreme events are only one of the many changes that the Caribbean is experiencing right now. The last 3 decades have shown one of the highest warming trends for the region, up to 0.2 degrees Celsius per decade, according to the WMO. Sea level rise has accelerated to almost double the global average in the last 2 decades. And the percentage of light corals has declined by over 50% in the last 5 decades. The figure that I'm showing here was kindly provided by the Climate Office of Puerto Rico. Shows the daily accumulated hours with temperatures exceeding 86 degrees Fahrenheit. The purple line that stands out above all of the other lines is 2024, which we know has been a record-breaking year. The Caribbean is very particular, not only because I'm from Puerto Rico. There's a very important, it's a very important part of the world. There's 13 independent island nations, 14 territories, including Puerto Rico and the U.S. Virgin Islands. It has a combined GDP of about 152 billion. It can account for the global 15 to 30% of the global ocean economy. A population of about 45 million, excluding countries in South America and Central America that border or have coastlines in the Caribbean Sea. Ecologically and biologically, it's quite unique, and it's often referred to as a living laboratory, and we're already seeing drastic changes to that. What have I done as a scientist to start addressing and understand better some of these changes and provide some meaningful solutions to the future? One of the things that I did was use the very same high-resolution CSM ensemble that Ping just presented to dive into some of the what projections are telling us may happen in the Caribbean Sea. We examined two periods, a reference period between 1986 and 2005, and the end of the century, to look at changes to different atmospheric and oceanic conditions. In here, I'm showing near surface temperatures of the ocean. And very strikingly, we found that the warming trend in these simulations is about 0.2 degrees Celsius per decade. And as you remember from 2 slides ago, that's exactly the trend that we're observing at the moment in the Caribbean Sea. What's noteworthy about this is that these simulations are under RCP 8.5 scenario, which we often refer to as the more aggressive scenario. And so for the Caribbean Sea, it seems that this scenario is not a highly unlikely case, but because it's very much what we're seeing right now. This slide, this figure shows changes in the salinity, the near surface salinity of the Caribbean Sea. A lot of projections agree that the salinity is going to become more saline. But what I really want to highlight in here are the spatial variability of the changes, highlighting the need for high resolution in terms of what the particular needs and actions that each nation in the Caribbean Sea should take are going to be shaped by this spatial variability. Salinity is changing by many contributions of different other processes, some of them related to the surface freshwater fluxes. We know that this ensemble and many other projections indicate that precipitation is going to be decreasing across the century in the Caribbean Sea, evaporation increasing, all of these contributing to a drier climate and a more saline Caribbean Sea. Now, as being showed, these type of simulations can be quite expensive computationally, and in many cases prohibitive to many institutions and researchers around the world. So towards that end, we developed one of the first regional ocean configurations within CSM, taking advantage of the new ocean model, MOM6. It's a 1/12 degree configuration. You can see here the surface temperatures and surface salinity. It was validated at seasonal to interannual timescales and showing really strong, solid results. So we're hoping that this can become a very useful tool to continue examining climate change impacts in the Caribbean Sea. And sort of my dream with this configuration is to eventually have it coupled to an atmospheric component and potentially a land component at high resolution so that we can continue to do impactful and meaningful science in the Caribbean Sea. And talking about that, and how CSM can advance regional climate science, I just want to highlight that NCAR has many great initiatives that one way or the other are helping develop and facilitate high resolution modeling capabilities, and I think we need to ensure that that support continues. Other partner institutions are doing the same. I also want to highlight the importance of collaboration frameworks and co-production. There's a really big need to bridge the gap between physical and social sciences to be able to reach out to communities that are facing climate change right now, to understand their needs and make our science really impactful like it should be. Two good examples of that are the Rising Voices Changing Coast project that has a strong collaboration with NCAR, and the Raíces initiative at the University of Puerto Rico in collaboration with NCAR also. The importance of this, in my view, is that regional climate science should target local needs. That's the main goal. And as climate modelers, we should start asking the question, not what can we model, but what must we model? So with that, I leave you guys. Thank you.
We're going to skip questions in the interest of time, but thanks very much, and I really like that last phrase. It's perfect, perfect motivation for us. So next we have Jonah, who's going to give a presentation as well. So Jonah is a PhD candidate at the University of Colorado, and this award reflects his multiple impactful scientific contributions, both developing and applying CSM. In particular, he has produced novel work on the climate impacts of mixed phase clouds in the Arctic, and on the seasonality and the emergence of the human-caused long-wave radiation signal in the Arctic. and as well as implementation of a satellite simulator in CAM to enable direct radiation to satellite observation model data comparisons. His work reflects both technical excellence and scientific depth and has earned him a NASA Finest Fellowship. So congratulations, Jonah.
Hi, I just want to kind of echo the sentiments of the other nominees today in that it is truly an honor to be up here, and it has been an absolute pleasure to be able to work with the CSM community during my PhD. As Dave said, my name is Jonah Shaw. I just defended my PhD at CU Boulder, where I worked with Jennifer Kay. And I'll be focusing on one chapter of my thesis where I developed a satellite emulator tool in order to make comparisons between CESM and these kind of direct spectral radiation observations from satellites. And when I say spectral radiation observations from satellites, what I mean are fields that are kind of measured in units of brightness, temperature, or radiance. And so these fields are specific to individual instruments up in space and how they respond to different wavelengths of light. And hopefully I'll be able to convince you that not only are these comparisons now pretty easy to make in CESM, but they're really valuable and insightful, and they're a great complement to how we already do our model evaluation. And I'll ground this by actually taking us back a little more than a year to a really awesome CLIVAR workshop that was hosted in Boulder and organized by a number of folks from NCAR. And it was all about confronting our Earth system models with the trends that our observations document. And the very first talk was an invited talk by Gavin Schmidt, who's the director of NASA GISS. And Gavin's talk was about kind of this art of comparing our models and our observations, and it was framed through a number of philosophical footnotes that Gavin presented to us. And so I just want to take the second philosophical footnote to try and kind of ground this presentation. In the footnote that Gavin gave us was all observations and comparisons are based on models too, or in other words, it's models all the way down. And what I mean by models all the way down is that many of the data sets that we treat as kind of a baseline in which to evaluate our models are actually themselves the result of some kind of inference or post-processing or aggregation step that introduces its own biases. And we should be really aware of all of these kind of hidden structural uncertainties when we evaluate our models. And one really excellent example of this is actually our reanalysis in satellite data sets, which I think are really some really bedrock data sources that we use to evaluate the performance of our models. And I'm going to argue that these data sets often disagree even when they are ingesting the same direct observations. And this is just one example. These are fractional trends in water vapor as a function of latitude and pressure from two different data sets. And you don't really need to know these specific data sets, but what's important is that they're both actually developed by NASA, and they both ingest the same set of direct observations, which are these direct spectral radiation fields observed by an instrument called AIRS. And so we can see that even though these data sets have so much in common, they give us entirely different pictures of what our trends are looking like. And if you ask, well, what about reanalysis? What about ERA5? It ingests a lot more information. It's a lot more complex. Well, if we add ERA5 to this picture, we again get a very different image of what our trends look like. And so I think this makes a good point that the differences between these data sets imply this large, unquantified structural uncertainty that's often hidden and really easy to ignore when we evaluate our models. It's a lot more work to evaluate multiple observational data sets. I also want to argue that these differences between our data sets are actually just a conservative estimate of the uncertainty because they only sample the kind of differences that these data sets have and how they do their inference or what they ingest, and they don't sample the uncertainties that all of these data sets share. And Ray Chemke visited CGD just a few months ago and I think gave a really excellent example in this paper that I'm noting here, and I think it's really cool to read. And so I want to kind of argue that in the presence of these large uncertainties, our spectral radiation observations, these kind of direct observations, are really some of the most complete and detailed observational records that are available, and that we should try to, in addition to the kind of standard evaluation of our models that we do, also evaluate them against these more direct observations. And of course, there's a reason that we haven't been doing this before, and it's because these comparisons are not easy to make. these radiation fields depend on individual satellite instruments and how they respond to these different wavelengths of light, whereas the radiation fields that our models produce are designed to iterate the physics of our climate system as accurately and as efficiently as possible and not to provide model evaluation. And so what we need is kind of an additional tool in order to span that gap and start making these other comparisons and kind of ask how much we can test or trust these other data sets that we often rely on. And so I built this tool in CESM, and we are effectively trying to bridge that gap and emulate these direct observations that our satellites would make within our Earth system model. And what's really great about CSM and a few other Earth system models is that they already have this satellite emulator program called COSP. If you're not familiar with it, it's another it's another software package that's built alongside the model. And as CESM runs, it has basically access to the instantaneous model state and is able to pass that state through these emulators that tell us, what would Calypso see in terms of clouds, or what would MODIS see in terms of clouds given the model state, and kind of account for these differences between satellites. Of course, we want to go a step further and evaluate the radiation fields and kind of completely sidestep this retrieval or inference step that kind of adds a lot of these uncertainties. And so what we added here is a radio transfer code called RTTOV. And just like COSP, it has access to the instantaneous model state, but it reproduces are these radiation fields that are not designed to iterate the physics of the model, but are rather designed just for evaluation and comparison against these basically direct observations that are often contained in level 1 satellite fields. And so we're able to run this emulator kind of in step with our model and in time, accessing the model state and effectively accounting for these different spectral response functions that our satellite instruments have at different channels. And what we get out of this field, or this tool, excuse me, are these satellite-like spectral fields, but critically that have intuitive meaning. And this is just a very kind of simple example to try and build this idea, is that on the right here, we have a surface temperature field from CESM, and on the left, we have something that looks identical, but is actually a spectral radiation field that's been produced by this emulator. This is effectively just a very transparent region of the spectrum, and we're only taking our rate of transfer in the absence of clouds. But the idea is that on the left, we have something that can be really fairly compared with this direct observable, and it still has all the intuition of the model state. Of course, I said this is a really easy example. We can move on to kind of other climate processes or variables that we're interested, like temperature in the upper troposphere, which is in the top right corner, and on the left is just another spectral channel that is much more opaque and is effectively sampling the upper troposphere. And so it's a really excellent proxy for that field, but again, is much closer to a direct observable. We can even think about things like clouds. So in the bottom right, we have our cloud field from CSM2, and in the bottom left, we just have a really simple proxy where I've taken the difference between our clear sky and our all sky radiation fields for this really transparent channel. And this is really just the thermal contrast between the warm surface and the tropics and the subtropics and the much colder emission temperatures from our clouds, but we can see that it's a really good proxy for the actual cloud field within our model. And so these are just two examples, and I just kind of want to make the point that these spectral observations, this instrument that I'm emulating here has more than 2,000 spectral channels. There's a huge amount of information in them, and these are some of the simplest proxies that we can construct, and there's a lot more that you could do if you're interested in specific climate processes. So whether these fields are of interest to you or not, I think there's value for this tool in so many different places. And once we've established this intuition, we can do just like very standard climate model analysis with these fields. So now we're looking at that field that sampled the upper troposphere, and we're comparing our observations from the NASA AIRS instrument from CSM2. This is in a region in the tropical Pacific, and we can immediately effectively identify a cold bias in our model. And we don't have to be worried about kind of uncertainties in the retrievals as long as we have that really strong intuition. We can move to another region. This is a mid-latitude region, northern North America, and we can start to interrogate the seasonal cycle and identify a very strong wintertime cold bias in tropospheric temperatures. And again, I think that the specific kind of physical processes are more meant to be illustrative in kind of trying to ground ourselves in that these comparisons are free of many of the uncertainties in our retrieval products. If we turn now to that cloud field, we can, again, just kind of apply this very simple analysis and see that our model is performing quite well in this tropical region with clouds, but is struggling much more in the mid-latitudes. And so what I mean to the point I mean to make here is that the standard methods that we have for model evaluation, whether it's you're perturbing your parameters, you're running a hierarchy, you're nudging, can all be applied to this tool just like CSM output. And so it's really a complement to the ways that we already evaluate our models. Another example that I'll kind of give, and this is a bit of a pivot, is that mostly I've been framing this in terms of how we can kind of use our observations to do a better job evaluating our model. But the benefit of this tool really flows in both directions, which is that we can also benefit the observational community. These are other spectral radiation fields, but they're emulated for this instrument called PreFire. And PreFire is 2 CubeSats that were launched a little less than a year ago. And the kind of novelty of these observations is that they're measuring, in addition to kind of standard 5 to 15 micron channels, also beyond 15 microns in this far infrared region that historically does not have observations. But these CubeSats, because of their kind of design, will only be up for 4 or 5 years, and so they don't have enough time to observe effectively internal variability or the climate mean state, a lot of the things that are really important to being evaluate our model. And so what we can do with this tool is emulate over a much longer time period what this instrument would see and effectively generate those statistics of internal variability or forced change on our side so that we can take those observations, put that in that broader context that an Earth system model can provide, and draw as much valuable information from these observations as possible. And I think this is a really kind of cool application for CSM2 in order to kind of partner with satellite missions. So to summarize, hopefully I've convinced you that a lot of our observational data sets have these structural uncertainties that are often kind of hidden and we don't actually fully understand, but that we can complement those comparisons by returning to the direct observations, which are these spectral radiation fields, which again are really information rich, they're globe spanning, and they go back multiple decades. And so it's just a way to complement our already the evaluation methods that we already do. And yeah, I think that's it. Thank you so much. And again, it's really an honor to be here.
All right, thanks. Congratulations again to Giovanni and Jonah and to Ping. So that concludes this morning's session. Please find Giovanni and Jonah and congratulate them and ask them questions about their talks and their careers as they're going to move forward now. So we're going to take a break. We're going to come back with a plenary session on sort of societal applications and integrating humans into Earth system models after the break. So yeah, let's thank everyone again, and see you out in practice. Okay, thanks everyone for coming back. Let's get started with our plenary session. We have 3 nice talks. We kind of put this together to be a set of presentations about sort of the societal, beneficial applications of CSM. So in the vein of this, we didn't really know at the time, but sort of we did, in the vein of the CSM use and impact. So we have 3 nice talks and by sort of different people than we've had at this meeting before, although Hansi has been a member of this community before, so she's moved on to a different position. So I'm really looking forward to this. It's going to be, I think, really thought-provoking and interesting. So we're going to start off with Hansi. So Hansi is the CSO and co-founder of Planet Incorporated, a climate tech startup specializing in year-ahead forecasts of environmental variables and extreme weather risks. Before Planet, Hansi led the Climate Dynamics Laboratory at the School of Earth and Ocean Sciences at the University of Victoria. Her group researched the physical climate system, particularly the myriad interactions between the atmosphere, ocean, and ice that give rise to Earth's climate. And she is an outgoing co-chair of the Polar Climate Working Group. So welcome, Hansi. We're looking forward to your presentation. Point to the screen for a second. Hold it for a second.
Okay. Oh, cool. Okay. Well, hello everyone. Thank you so much for being here. It's like super exciting to be on up here addressing y'all on this 30th anniversary. So I'm going to talk a little bit about my journey, particularly from being an academic scientist and a researcher to doing things in the real world, which is messy and crazy, but to me, it's been amazing, and I probably feel like I should have done it sooner. So you'll see. So before I get started, I want to get out a few shout outs. So first of all, it's Pride Month. Happy Pride Month, y'all. And yes, okay. And it's 2025, but guess what? Black lives still matter, so we support that. And two more really key shout outs to your colleagues at NOAA and NSF who might be dealing with a lot of drama and storminess in their lives right now. Please give them a hug if they like hugs, okay? And say thank you. I'm really grateful for all of the work that they do, who have made so much science possible in the earth sciences. So today, I'm going to talk a bit about my career story, how I decided to found Planet AI. I'm going to talk about AI for the earth sciences in general. I'm going to talk about taking the leap into the real world from the academic and research world. I'm going to talk a bit about the business of forecasting, and then I'm going to offer some unsolicited advice, particularly for early career researchers who are interested in making the leap into the real world. So this is my career timeline, and it looks like the career timeline of a squirrel. Like if a squirrel could have a career, this is how they would have the career, because they would jump from one thing to the other because they couldn't decide what they wanted to do. And that's pretty much what I did. So I got my BA in physics from Rice in the last century, which is kind of scary. And then I spent a bunch of time in the real world, dancing, traveling, doing some small business entrepreneurship, starting a family. And then I did my PhD in atmospheric sciences with a master's in applied math at the University of Washington. Finished that in 2015, spent some time with the US Department of Energy as a Linus Pauling Fellow. And then I was an assistant professor in the School of Earth and Ocean Sciences at the University of Victoria. And at that time, that's when I decided that I wanted to start a company, found an amazing co-founder who I will talk about in a bit, and decided to just, got to the edge of the cliff and decided to take off. So that is sort of the overview. So career of a squirrel, here we are. So what is Planet? So Planet is a mission-driven climate tech startup. We are committed to build climate resilience around the world using a combination of the latest science and the AI. So far, we've gotten over $3 million in funding. We have 5 team members. We have 15 B2B users, and this is growing. Not all of them are paying yet, but we're going to make them pay. And then we have expert advisors, some of whom are sitting right in this room today, which is amazing. And then, we have training data, because you know what? This is one thing that us earth scientists are really good at making, so much data. So we have tons of data. And so one day we will train on all petabytes of it. And just recently, we became an NSF SBIR portfolio company. So that is super exciting. So thank you, NSF, once again. And amazingly, we didn't get our funding pulled, so. So a little bit about our founding story. So this is Dr. Kalai Ramea. She is Planet's co-founder and CTO. I'm CEO. And so whenever you start a company, there's always a founding story. For both of us, I was sort of moping around at the University of Victoria. This was around 2022. Kalai was a technical director at that time at Xerox PARC in scientific AI. And so, we were introduced by Dr. Phil Rash, which many of you all know. And he was like, Hansi, stop moping around. Here's a friend. Make a friend. She does AI. Do something cool with her. And so we did. We actually got together and wrote a proposal for DARPA and got $1 million to spend from DARPA and led some cool projects on geoengineering, and particularly geoengineering teleconnection emulators, which, sure, maybe in some future sci-fi world, you might be able to use them to, create your optimal geoengineering forcing in order to, produce the desired climate effect. And I have to keep track of the time because I talk a lot. Okay. And so we got this money, and as soon as we got this money, we're talking every day. I literally talk to Kalai more than I talk to my husband, which is kind of crazy. And so, started talking, and we're like, oh my gosh, we need to bring some of this into the real world, because great that DoD gets to play war games with emulators, but there's so many other uses of this science. And so much of it hasn't quite made it out from the research world to the real world. And so that's what we decided to do. We decided to start Planet. So the paradox of the earth sciences is the fact that it is a science, and science is all about research and empiricism. And it's fun to know just because you want to know. It doesn't even need a reason, right? I mean, that is basic science. At the same time, today, we are sort of in a global environmental crisis. And therefore, society really needs our science. And so both of these things are happening simultaneously. And for many of us, it's possible that we actually do earth system science because, we first got into it because we were like, oh, I think society really needs this. I know for me, I started in math, and I came into the earth sciences because I was like, oh, this is societally relevant. You can actually use math for cool things that matter. So the challenge here, of course, is that we have to bridge the gap between what science wants, which is rigorous, empirical, reproducible inquiry into just how the world works, without necessarily any practical applications other than the fact that it's cool, and then what society wants, which is insightful, valuable technology that solves something that is a problem or a pain point for them. So this is actually, this bridge, that's what companies do well when they work well. And so this is what, our goal is, to be able to bridge this gap between science and society. So what we did was we had hundreds of conversations with folks in a whole bunch of different industries to try to understand what is it that these people want. And, the thing is, I am a nerd, and I work very, particularly on nerdy things and computing and math. And so, I might think I know what people want, but I don't know what they want until I talk to them and I listen. And so this is what we did. And there were many insights that we got by just having a ton of these discovery conversations with people in a whole bunch of different industries. So some of these people were just friends. We were like, hey, do you want to know anything about how your house might be underwater in 50 years? And they were like, no, please don't tell me that information, because I just outbid 10 people to get my house. So please do not tell me that. So, we talked to friends like that. And then we were talking to insurers, we were talking to farmers, we were talking to reinsurers, we were talking to logistics folks, we were talking to data center folks. We talked to so many people. And so there were some things that we learned just kind of generally about how climate information is used. So first of all, I know we love longer term outlooks, but the kinds of outlooks that people want to hear is not scientists scolding them necessarily. We should scold them. Don't worry, we should. Let's keep scolding people about long-term outlooks and how dire things are. But people also need practical information, and that practical information is the nearer term information. It's not the, let me tell you what a mess things are going to be in 2050. Nobody wants to really hear that, and they might not even want to pay you for that. They probably don't want to pay you for that, in fact. So what people want is nearer term information, and they want good quality nearer term information. Who wants this? Well, people that need better environmental security. There are many industries that are extremely environmentally vulnerable. Think about forestry. Think about farming. Think about insurance, which, in the state of California, insurers are running around like chickens without a head. And, this is happening around the world and in many different markets. And so, people want a little bit more certainty. People also want information that's insightful more than they just want raw data. If they wanted raw data, maybe they would go to NOAA, right? But they want actually insightful information that can tell them very particularly things about their industry. And then they want these insights to be packaged in a way that is understandable to them, because not everybody is a data scientist, not everyone's going to pull up Python, not everyone is going to, be able to understand your, giant data file that you provide them in NetCDF format. So you really got to make this so that it is usable. So this is how society sees future outlooks. I know this is not actually where the science is, but this is how people see it. So what they see is like, okay, I got these weather forecasts on my phone. They go out to 10 days. And then they hear on the other side all the scientists being like, things are going to get really bad, and they're getting bad, and, what are you guys going to do? Stop emitting, right? Which is great. They should hear that. But people literally don't know that there is actually science that can address forecasts beyond 10 days. That's just something that unless you're an energy trader or someone that is in maybe Citadel, unless you work at Citadel or D.E. Shaw, or unless you're an energy trader, you literally think that this is impossible. And in fact, when I was first going around pitching Planet to venture capitalists, they were I think they literally thought I was Elizabeth Holmes. They were like, are you messing with us? Because we don't think that anyone can do this. And I was like, scientists have been doing this for 20 years, y'all, right? But the problem is that we're not good at communicating this stuff. We're not good at operationalizing this stuff. We're not good at giving this information to actual humans in a way that they know that it exists and that it solves their problems. And so this is how our work fits in. So we fill this S2S gap. We provide forecasts from next week. Our goal is to eventually go to 5 years. I'm telling you, humans are like squirrels. We pretty much don't want to know anything beyond a year. So, that's about the sweet spot. Next week to next year, that's where people want to know information. And beyond that, it's sure, maybe if you're a forester, you're like, yeah, my trees take 30 years to grow, guys. So you might want longer term information. But in general, this is sort of the time scale that people think is important to them for their decision making and where they wish they had more information. So there are huge opportunities for AI in the earth sciences. So we know that weather forecasting has really been revolutionized by AI in many ways. It has a long way to go, of course, but there's been huge leaps and bounds and advances. So the big question is, what comes next? So where else can AI be applied in the earth sciences? And I would say S2S to D forecasting is probably one great area where AI can be applied and make a great difference. So in terms of these different opportunities, first of all, we have training data. We have petabytes of training data available for models to learn dynamics. So, you just got to train them, right? Earth system model output, satellite observations, maybe even sparse measurements so that you don't even have to rely on some sort of analysis product, right? So many different data sets to use. And then there are so many different architectures. Now, please don't ask me any details about these architectures. If you would like to know details, our machine learning engineer, Anisha Paul, is right here. So make friends with her. She has a name tag. Anisha, raise your hand. Yeah, thank you. And she is amazing, and she is the smartest gal you'll ever meet. So talk to her if you want to know real machine learning engineering. And so many different ways of creating your machine learning architectures, so many exotic, weird operators and nets, transformers. I thought that this was a toy, but it's not a toy. It's not a robot. It's an actual architecture. And then latent space representations as well. So, and then there's so many different modeling approaches, right? You could do brute force training, but you could also use physics-informed models. And then you can also use foundation models to learn the real way in which a system operates using a ton of data. And so that's where that petabytes of data come in, and that's where, NSF is we want to fund you for this. And so that's why we're an SBIR company. So how do S2S forecasts inform businesses? So there's many different ways that they can. And so let me walk through this kind of different ways that information can be presented. First of all, there's just the raw forecasts, and these are for users that are extremely data savvy. So if you go and you work with like D.E. Shaw, right, they have like an energy trading division. These people already use NOAA forecasts and ECMWF forecasts. So, you know, they have algorithms. They literally will not tell you anything about what they do other than they're doing something with energy because they don't talk. And they will use your forecasts. Like that's it, right? But most people are not D.E. Shaw or your neighborhood energy trader. So they need a lot more help. So this is where perhaps generic data layers might be useful. So instead of telling people, this is what we forecast the temperature to be, we then say, okay, this is what we think the heat index might be, and this heat index might be not good for your outdoor workers. You might be putting them in harm's way. And so, you know, you're providing them a bit more insight than just the raw data. And so this is for users who might need basic weather insights for making their decisions. And then finally, at the very end, you know, you might provide more tailored insights using customer-specific data. This is where you get into a lot of, you know, potentially security and data compliance issues. So this is an area that we're very careful in, and we haven't quite gotten to that area because then that means you're saving customer data, et cetera, and that is, you know, highly regulated. But basically, this is for people who need insights right at the intersection of weather and their business operations, and they need very, very, very specific information. So think about like a logistics company. They might have all of the different nodes of their supply chain, and they might want to know, hey, you know, tell me how I should design this in such a way that over the next year, you know, I am least likely to have weather disruptions, right? So this requires a lot of, you know, knowledge from them on their specific operations, and then it requires using the weather data on top of that. So our customers are in sort of many different areas. So finance, those are real fun customers there. Insurance, shipping and logistics. This is a pretty cool area, especially if you like maps. Utilities, that is a tough nut to crack, y'all. Yeah, I don't know. If someone knows the secret to working with utilities, let me know, because yeah, we have a utilities customer, and they're tough cookies. And then humanitarian organizations. So we do a ton of pro bono work with humanitarian organizations, and in particular, humanitarian organizations that work in the developing world. And the reason why is because, as we know, climate change is a huge environmental justice issue. In particular, the effects of climate change, as we all know, are, you know, much more dire in the developing world, not only because of fewer resources, but sometimes of even greater impacts. And so what we do is we provide forecasts, S2S forecasts, to various NGOs that operate for humanitarian causes in the developing world. So we are working with NGOs in Ethiopia and other countries in East Africa. We are also working with NGOs in South Africa, particularly dealing with malaria, because malaria kills a ton of children. And guess what? Like, if you know when the rains are going to start, you can actually like spray properly for those mosquitoes and get the maximum bang for your buck. Because once the rains start, like, you're out of luck. Like, you're going to have, you know, an outbreak and children will die, right? So it is like totally essential to be able to get information like this to folks. And this is an area where like we are super committed to wanting to do better in terms of really being able to predict the beginning of the twice-a-year monsoon rains that you get in various places in Africa and South Asia. And then we are also working with some big NGOs, including Mercy Corps. So this is like super meaningful work, and we do it for free because it is insanely important. And you know, the reason why we can do it for free is because guess what? We make the rules, right? That is the beautiful thing about having your own company. You can do what you want. You do what you want whenever you want it, right? And so I can literally like build my own version of capitalism the way that I want to. And if that includes, giving free things to people that should get them for free, then we do it. That's it. So some unsolicited advice. First of all, I know we think that we know everything, but we don't. Please listen to people to understand what their problems are. You might hypothesize that they have a problem, but talk to them and figure out if it really is a problem. Because if you don't talk to them, then, you're just going to think something is a problem, and then maybe you'll build something for them, and then they're like, nope, this is not a problem, and I'm not going to use this, right? Which is kind of not great. So make sure you listen to people. Work directly with stakeholders or interested parties, if you want to say it that way, or work with somebody who does. So, there are some, sorry, keep on checking the time to make sure that I'm not going over. There are some foundations, I'm not going to name any, that have a ton of money that do work in the developing world, and they literally come down, they swoop down, and they say, y'all need this. And they literally, sometimes spend millions of dollars on whatever this is. For example, some sort of GMO plant that they're like, hey, you should plant this because it's drought resistant. And, climate change is causing a lot of drought. Well, guess what? They never talk to the farmers. And the farmers, it turns out, they're like, no, we're not going to do any GMO plants. And so literally you have solutions that are built and then are just languishing because no one actually bothered to have a conversation with an actual farmer. Okay? So don't be like that foundation. And then finally, find a complementary buddy to work with because, I got my co-founder who is like my best buddy, who I talk to more than my husband. But it's great to work with other people. And, I think that if you were going to start a company, for example, it would be real lonely to do it by yourself. So find a friend. Find a friend and make sure that they're complementary because if they're just like you, that's, not quite great. So these are some of our, this is a photo from our recent trip to the Ethiopian highlands in Gamo district. This is near Arba Minch, and this was in April. And I think that this kind of includes all of those elements here. So I'm there with my buddy, who is CTO of Planet. And, we are talking directly to farmers in the highlands. You can't see them, but on the other side of that photo is a translator. And so we directly ask questions about their farming practices, about how S2S forecasts might help. What kind of information do they want? That's when we learn the start of the rains is really important, or how long the dry season is going to be is really important, or, how much might it rain this year? That's super important because then, they can actually determine what crops to plant, for example. So I think that having that opportunity to talk to the real people that are impacted by the work that you do is just priceless. So any opportunity that you get to do that, you should do it. So founding a startup is great, but it's also terrifying. It is magical and terrifying at the same time. So first of all, as I said, I can do what I want. So we can provide free forecasts, we can provide paid forecasts, we can do whatever we want. We can create a new business strategy and model, and we can run it our way. Okay, great. But at the same time, it's like a very lonely journey. Even if you have a co-founder, you get obsessive and compulsive, and your family is like, "What's wrong with you?" You get really rewarded for a job well done, which is great. I feel like sometimes in academia, people don't. But at the same time, you're constantly stressed out because you're in charge of so much stuff, right? So this takes a special kind of person, kind of a masochist. But if you are that masochist, and you need advice, you can talk to me because, I think it's really fun. I think that this is true, but at the same time, I feel like, the rewards are worth all of the pain. So even if you're not a masochist, there's so many cool things to do out there in the real world. There are so many big companies that need Earth system science. They need your expertise. So go talk to them. And this is not just big companies, right? There's so many nonprofits out there as well. People doing great work. And then, of course, there's all these small and growing companies that are trying out new business models, new ways of doing things. work for one of them, or at the same time, if you like to build new things, there are so many new companies to build because there are huge opportunities here. People need this information. I think that that is sort of the crux of it. So thank you so much. And yeah, I did not run over, so that is good.
Thank you, Hansi. Excellent. Any questions or comments for Hansi? Kyla?
You emphasize that people don't want to make decisions based on long time scales, but I kind of feel like they should be. Do you see there being a role for you not only listening to people what they want, but also trying to persuade them that there is this information that they should be factoring in as well?
Yeah, I agree with you that there's information that they should want. But to some extent, I think that presenting them information, say, beyond the weather scale, it starts to get into that kind of longer term information, right? Because, I mean, one of the reasons why I think S2S forecasting in particular is potentially so critical right now is because of the fact that weather that people used to think was normal is no longer normal or expected, right? And so because of that, you're automatically having the climate change conversation, even if I'm talking to a banker that doesn't believe in climate change, right? So we have to figure out ways to get in with these people, and I think lecturing them is not going to do it. So when it comes to people's like bottom lines, that's kind of where it actually hits people and where people are persuadable, I think.
It's coming to your 1 petabyte of data, and I'm just wondering what the mix of that data is.
Yeah, totally. We love CSM.
Is it all, is it observational? Is it data to be trained on? Is it actual forecasts? Or just interesting?
Yeah. So for training data in particular, CSM is a treasure trove. And as you saw earlier today, CSM2 is one of the best Earth system models out there, right? So why not use it? I mean, if we're particularly, concerned with variability, then, it has a lot of it out there. So Aiden, Dr. Aiden Sweeney, who's right here, Aiden, yeah, there he is. He'll be presenting a poster on training a AI model for ENSO using CSM. And I know people complain, they're like, oh, ENSO and CSM is not good. But guess what? We produced a model just using that data that predicts ENSO amazingly well. So if you do, all of the back testing, the hindcasts, and look at the ACC. So yeah, CSM is where it's at. Of course, there's other good models out there too. CSM is the best.
Hi, thanks for sharing your story. I was wondering if you can expand on the tough nut to crack with the utilities, and maybe more generally, do you encounter potential partners that are skeptical of model data in general, but really like observations and want to rather rerun the worst drought of history rather than trust any climate model looking forward?
No. So the major thing, answering the second question, in general, sure, people want quality data, but the people that want the highest quality data, those are the people that are like the hedge funds. So if you want to sell data to hedge funds, then sure, shoot for we want amazing high quality forecasts. For most people, they're functioning on nothing in the S2S to D time horizon. And so for them, if you start talking about quality, you are ahead of yourself. You are way ahead of yourself. They literally just want some kind of insight into the future that has skill, right? So there's that part. I think, sorry, what was your first question? The utilities, right? Yeah, utilities are very conservative and they don't like new things. And, I think for a lot of them, they have not really wrapped their heads around climate change. So there's one utility that we are working with, and I don't know. My hunch is that they look at forecasts and pray. That is all I think they are doing with the forecasts. So there we are.
Okay, thank you.
Yeah. Thank you.
Okay, so next up, we have Paula Buchanan. Dr. Buchanan is a practitioner academic, a pracademic. Is that your term? I like that. A sociohydrologist and disaster and emergency management researcher. She researches sustainable drinking water access issues, focusing on the intersections between public health, risk and science communication, sociology, and emergency management. As a sociohydrologist, her research focuses on how people interact with drinking water systems and human behavior's impact on these systems that support drinking water to sustain life. As a self-proclaimed data nerd, Dr. Buchanan is also passionate about using data science, information technology, and data visualizations as tools to more effectively communicate with target audiences. So welcome, Paula.
And thank you to Hansi for adjusting the microphone for someone who is also vertically challenged. I greatly appreciate it. Hello, everyone. Okay, I'll try this one more time. Hello, everyone. Okay, yeah, you're awake. And thank you for adjusting that for me as well. Thank you. As Dave said, I'm Dr. Paula Buchanan, and I swear I only met Hansi today.
Could you get a little bit closer by the mic?
Get towards it. I'm so used to moving. Sorry, guys. So yeah, I just met Hansi today, but we have so many similarities about what we think about, and you would almost think, I was discussing this with a colleague in the back, that we had planned our slides and our content together. We didn't. We just think alike. So yes. So the title is Bridging the Gap, from Hansi, Communicating Earth System Science to Stakeholders, Communities, and Decision Makers. So this is what we're going to be talking about in the next couple of minutes. Going to give you an introduction, going to talk a little bit about that topic of SciComm or science communication. I'm going to give you some tools and tips that you can use in CESM, SciComm tools that I've used in the past, and bridging the SciComm gap. I'm going to give you a really cool, neat sample example of using SciComm that I have used in the past as a sociohydrologist. Going to do a conclusion, and hopefully, if I can get through this quickly enough, some time for Q&A. So let's get started. So, introduction. So, I see this as a theatrical performance, right? We're on stage, and I am Act 2. We got our Act 1, we got Act 3 coming up. We're right here in the middle. We started talking about system predictability. I'm going to be talking about communication. Then there's going to be someone coming and talking about human systems. So I am that bridge. Again, the concept of the bridge. Communicating science, as I call it, SciComm for short, for real world impact. Because the science that we do, it could be fun, right? But you'll see me, I'll say this a lot in this presentation. So what? It's one thing my dissertation chair used to always say. Oh, that's really cool that you want to, when I was in public health, for example, you want to look at obesity and the connection possibly between this and obesity. So what? Who cares about that in the real world? It's kind of cool and neat to do, but like, what are the practical implications? And that's something we have to really start to focus on. So a little bit about me. Yes, both of those pictures are me. The first one is me. I participated in a program in the city of Atlanta where I'm based called the Citizens Fire Academy. It's a place where, it's a program where people who are residents of the city can actually go through fire and EMT training. And so that is me in full turnout gear in August in Atlanta. It's about 20 pounds. And if I put in the oxygen tank, it would have been another 25. So yeah, and I managed to smile. So that's me. I also worked. That's why I'm going to call out Hansi again. I actually worked for the City of Atlanta's Department of Watershed Management. That is me actually in the field doing a sludge judge, as we call it. So I've done work with fire, EMT, and of course in water. So as Dave said, I call myself a pracademic. I'm a practitioner academic. You might also hear people call like a practitioner scholar. It's basically the same thing. My doctorate is actually in emergency management, so I do focus on disaster and emergency management, sometimes called EM, sometimes called DEM. And I'm also a sociohydrologist. How many hydrologists are in here? Just curious. You too? Oh my God. Who else? Like, keep your hands up. All right. Who's a sociohydrologist in this room? Okay, it's just me. There's just me. Yeah, we're pretty rare. So my background is actually not as a hydrologist/engineer, it's as a sociologist. So I'm the person who deals with the people who are going to be using the systems that, say, a Dave would make. I do the UX to make sure that it works properly. As Hansi was saying, you have all this great technology out there, but did anyone talk to people about how it's supposed to be used? That's very important. And then also I do a lot in the SciComm or science communication space, which is why you guys wanted me here today. So let's talk about science communication. Gonna do a little bit of a deep dive. So what is it? It's sharing your knowledge, right? It's communicating with stakeholders. And it's a personal story. A lot of us are scientists because we're passionate about something. Someone might want to become a cancer researcher because their parent or a loved one died of that same cancer. So we all have these personal stories about the science, but then we talk in a very, what I call, wonky way, right? We use all these fancy acronyms and words, and we have to remember why we started doing the science in the first place, you know? Why is it you decided to be a researcher? Why did you decide to be a sociohydrologist? Why did you decide to be in public health, and so on? So yes, we're going to be showing the outcomes, then the results, right? And again, as one of my dissertation chairs would say, those biases, assumptions, and limits, you got to put a fence around those. What is your fence? Because if you're looking at cancer, what type of cancer, and so on. You have to put that fence around what you're doing and then what biases, assumptions, and limits you have based on what's in that fence. And then again, I'm going to keep saying this. So what? Okay, you're doing this really cool dissertation. You're going to be doing all this stuff with GIS data. So what? Why would my grandmother care? Why would a 3-year-old care? Why would a family that's poor and like living on the edges of society or living in the global south, like Hansi was talking about, why would they care? That's very important. And then you also have to think about how SciComm translates into science policy. The science policy of so what? What are those actionable steps that will be taken, hopefully, ideally, if you are good or effective at science communication? How can your science be communicated so people care? They don't ask, so what? They just like, okay, what can we do? What money can we give you to continue this research? What policies and legislative actions can we take to support what it is you do? So, why should everyone in this room, CESM people, care, right? Without effective communication, without effective science communication, science fails to influence decisions or the science policy. You're working in a vacuum. It could be really fun, but it's more navel-gazing, and you're not making an impact on society. And I think that's why a lot of people become scientists, right? So you have to think about that. You're failing to influence decisions. Again, the so what? I called myself a practitioner academic, a practitioner scholar. My research, from my perspective, whether I'm doing emergency management, whether I did public health in the past, whether I'm doing sociohydrology, working with water utilities, my research is used to better inform practice. It is not in a vacuum. Practitioners should be able to take what I'm doing and use it. Or even better, I communicate with those farmers, Hansi, like you were saying. I communicate with the water utility people, and yes, they're conservative and can be difficult, so we'll talk later. But yes, that's so important. What is it that we can do to help you as opposed to I alone can fix you, right? Sound familiar? So stakeholders must understand the research that you do in order to find it valuable and also to use it. So, science policy, why should you care? You're a scientist, you don't care about science policy, right? That's wrong. As a scientist, you should care about policies that impact the research that you do. Science policy connects that science to the so what, the actionable steps, government decisions, public policy, and also laws, like I was saying, legislative actions, and funding to support the research that you do. So the science, you use SciComm, and then that translates into science policy, which then can be used to further fund science. So it's almost like even though it's linear here, it's almost like a little bit of an oblong circle. You're just kind of going in like a flow, so to speak. And what you do here at CSM is some nerdy stuff. I remember when my colleague actually asked me to look at like what some of the work, and I was like, wow, this is wonky. It's cool, but it's wonky. It's hard to digest though. And so it's really important to take all these complex models and translate them into something that is clear, understandable, and actionable, whether you're 90 years old or 9 years old or 29 years old. That's really important. Transform that so what into an action. So I'm going to give you a couple of case studies of SciComm, or science communication and practice. As I was saying earlier, I actually used to work for the City of Atlanta in the Department of Watershed Management. And for those of you who know Atlanta, who's been to Atlanta before besides just going through the airport? Yeah, it's a big place, isn't it? It's a little intimidating. It's sprawling. It's big. Yes, that's Atlanta. It's a big urban city environment. It's also, interestingly, from a DWM standpoint, it's a huge urban forest. One of the things you'll notice, there's a lot of forest, like 5 minutes from downtown. And there's watershed issues aplenty. Whenever it rains, it floods. The infrastructure is trash. It is, because people don't want to pay the money to get it retrofitted. So one of the things that my office decided to do when I worked for DWM was to create a public education campaign. So as Hansi was saying earlier, there's all that earth science data out there, right? We at DWM had a lot of data. So what are we going to do with it? We're like, okay, let's flip this a little bit. We're actually going to take this data and look and try to figure out what is the human impact of water systems, right? What is it that we do as human beings that negatively impacts the watershed that we have, the urban forest that we have, and then how could we educate and train people to improve their behaviors so that our watershed is more sustainable. And so that's what we did. We had all this water data, we analyzed it, we talked with community leaders, and we actually started improving the watershed through the Safety Ambassador Program. I was in the inaugural class of it. I really enjoyed it and loved it. And it's so important to have programs like that that get people, everyday people, engaged in the research and the science that we do. And now I'm going to pick on you guys, right? Because I'm here. So you're a case study here. You got this complex data that you're trying to translate into actionable insights for stakeholders. So 2 ways you do that. You actually have been able to mitigate urban heat issues. Good for you guys. Clap for yourselves. Come on, you got to be your best cheerleader to get people. Come on, clap for yourselves. All right. And you also use that climate data to improve one of my areas, water resource management. Second clap. Yes, yes. So you're already doing some of this. It's just you have to think a little bit more on how you could do it so it has more impact. So you're already ahead of the curve, which is great. So some tips and tools for you and the audience to learn how to be awesome SciCommers. So first of all, you have to think about what type of media you're going to use, right? There's traditional or legacy media, as it's called, print, radio, lectures like this, right? That's fine and dandy, but I can say this as someone who is older, it doesn't appeal to the young people. It really doesn't. You need to think about other ways. You have to think about multimedia. Even though I'm not the biggest fan of podcasts, they're really popular. They're really, really popular. Think about podcasts. Think about photography. That's actually a more traditional media, but there's ways that you will see, spoilers in the presentation, where you could use photography and illustrations. And then you could also make videos. We're going to talk a little bit more about that later. So there's all different types of tools you could have in your toolbox, but I'm going to just focus in the interest of time on 3, and I've used all 3 of these. Having cross-functional teams, knowing your audience, and storytelling. So first of all, cross-functional, or as some people call them, interdisciplinary teams. So like disaster and emergency management, which is my field, earth sciences deals with what you call those wicked problems. You've heard people say that before. They're really complex. It almost feels like when you're doing research, you're almost doing whack-a-mole. As soon as you like push down one way, it goes up another way. People are involved and human behavior is involved, which means it's gonna be a wicked problem. There's just all these different things you have to deal with. So we're dealing with complex wicked problems. So it's important to have the scientists like us around. But it's also important to have community member input. You know, as Hansi was saying earlier about the farmers, if you're going to be doing something with farmers, you should probably have some dealings and interactions and trustful relationships built with those farmers. You need communicators like myself because we help to translate your science into something that more people can understand. We're going to need the modelers because I can do a little modeling, but you know, I'm dangerous in a bad way when I do modeling, so need you to do that. You need the practitioners, the people with their boots on the ground doing the work, and you also need project managers. I actually, that's, in full disclosure, I love being a project manager. It's one of my best jobs ever. I love it, even more than doing the communicating, so shameless plug for the importance of project managers. So when you have these cross-functional teams, you basically see those wicked complex problems through more diverse lenses, more diverse perspectives. And when you get all of those different perspectives together, things make more sense. You understand more effectively those wicked problems. And this is really important, and this is why I put it in the middle, because this is like the meat of the three. Know your audience. You have to know how to communicate with people. For example, if I am doing this talk on science communication to 6th graders, this is going to be really different. There will be one thing that will be exactly the same, and I'll see if you can figure out what that is, but it will be very different for 6th graders to seniors at like a convalescent home. It's going to be very different. So you got to know your audience, know their culture. That fosters trust. Trust is key. A quick sidebar, ever since I finished my dissertation, I started doing some work with tribal nations, indigenous populations, and that's a hard nut to crack because understandably, they don't trust us. I get it, right? But now, in my Rolodex, I have about 5 or 6 different people from different tribal nations that will call upon me and my expertise because they trust me. And forming those relationships is hard. It's complex and it can take years, but when people trust you, they're more likely to work with you and believe what you say as a scientist. And I don't know if anyone knows Dr. Raj Pandya. He used to work for American Geophysical Union. He's now at Arizona State with Michael Barton, who is right there. And this is one of the things that he always told me. He's one of my mentors. When you go to these community meetings, you show up, preferably on time. Most importantly, you shut up. And you, like Hansi was saying, you listen. You are there to listen. You are not there to say, only I can help you with this. No, you are there to listen. And bring good snacks. Always bring good snacks if you can. That's like a great, food is like people open up when you bring them food, especially when it's good. So speaking of which, knowing the culture, give you a sample example. Who in this room knows what a challenge coin is? I see one. Anyone else? All right, sir, would you mind telling me your name? Steve Rabin? Sam, okay, forgive me. I'm like old and my hearing's bad. So Sam, question for you. What is a challenge coin? Yes. So I'm going to give the crib notes. So a challenge coin is something you see in the military, and it's a little piece of metal. It looks like Franklin Mint-like stuff. It's not worth anything monetarily, but it's worth a lot in emergency management, which has a lot of people from fire, EMT, law enforcement who have a military background. And what you do is, it's a way to say, so Sam, guess what I got for you? I know it's hard to see, but this is a challenge coin. And if someone would mind bringing this to Sam, thank you. So that little hunk of metal in my field of disaster emergency management means more than any degree I have ever gotten. No joke. So I understand how important those are to the people in my field, and I actively trade them. I go to conferences sometimes just to trade coins, and I'll show them pictures of my collection, and they're so impressed. They don't really care about the doctorate or the MBA. Oh, you have a challenge coin from the White House. Wow. So that's a good sample example. And I will say, if anyone's like online, because I know some of y'all are, look at the Wikipedia page for Challenge Coin and learn about it. It's really a fascinating culture. I almost did my dissertation on it, but I never served in the military, so I felt like I would be kind of like a little bit of a poser, so I didn't. So knowing your audience, it builds credibility with you, and more importantly, the science that you're talking about, right? Science communication must resonate with the audience, not just inform. It must inform. And then storytelling. If anyone has kids, grandkids, nieces, nephews, is an auntie or an uncle, you probably hear kids say all the time, tell me a story. Everyone loves a good story, right? Everyone loves a good story. So I know there's a whole bunch of map nerds in here, so I'm not going to call you all out because it might be the entire room, but raise your hand if you know what Esri story maps are. Okay, there's a few. Keep them high. I want to see. Okay, who's actually, of the people who have your hands up, who's actually used them? One. I see one. Okay, I might have a challenge coin for you later if you come find me, because thank you for using those story maps. This is one of the coolest, wonkiest things that is, in my opinion, an effective science communication tool. It's called Esri Story Maps. You can take all kinds of data, put it on maps. You can put qual data in, quant data, totally mixed methods. You can put in visual elements. So you see there's maps, there's high-res photography like I was talking about. The link is right there. I don't know if they're sharing slides later, but it's called The River of Resilience, Esri Story Maps. You can look it up. And they're really, really neat. You want to see me like nerd out? Get me on some story maps. So as a result, I found out somebody else has their own story map. So there was this organization called the Community Climate System Model, CESM's predecessor. Look at that. You already have been doing it and might not have even realized you've been doing it. So this is a large-scale model, right? Made into these wonderful-looking story maps. So I challenge you all. Let's make some CESM story maps, right? They're fun, trust me. So we're gonna go on to bridging the SciComm gap, a SciComm to science policy sample example. So as I was saying, I've done work in the water space, worked for the city of Atlanta, I've done SciComm, and so I got a little tiny piece of funding to do some SciComm to better inform science policy issues in the city of Atlanta. And so what I did is I produced and animated my first short film. Yes, I did. It was so much fun. Called it The Attack of the Evil Fatbergs. So this is a science communication, a SciComm product, an animated short film that impacts and informs science policy, and that was specifically drinking water infrastructure, which we talked about. So I'm gonna actually show you the 2-minute film if we have time, but just in case the technology gods do not like me today, I want to give this to you. It's on YouTube. The QR code should work. There's also a bit.ly, a short URL there. And so let's get into it. Fingers crossed. Everyone cross their fingers. Let's see if it works.
There's a monster lurking in your plumbing, and you may have been unwittingly feeding it.
In most kitchens, it's common to find fats, oils, and grease. Unfortunately, in many kitchens, these fats, oils, and grease end up going down the drain.
The hungry fatberg waits to feed on these fats, oils, and grease. The more you pour, the bigger it grows.
Until eventually, or worse, all these little fatbergs may join forces to clog pipes backing up sewer systems. Fatbergs threaten our water supply by dirtying water and straining water infrastructure.
What can you do to fight fatbergs? Well, I thought you'd never ask.
Responsibly collect your fats, oils, and grease. Safely dispose of them. Together, we can defeat the fatbergs.
That's the so what. That's my name. Wow, thank you. So I was watching the crowd, and I always there's a young lady here who's wearing a black and white shirt. You look like you've gone back to childhood, and it's like Cartoon Saturday here in the United States. See what that did, that 1-2 minute film, right? I went and got the money from AGU and from the Union of Concerned Scientists. I think I directed and produced it for about $800 to $1,200. I mean, does that look like that's like that cheap or inexpensive? No, but I figured out a way to make it work. So thank you for enjoying my film. And if you do want to look at it, it's on YouTube. So just wanted to say that. So recap, getting towards the end of Act 2, my act on communication. So science and the science that CESM is doing is important. So is getting the message about that science and what it can do. The so what, the science communication is also important. So effective science communication is essential to translate that data into action. So a quick conclusion, we should always ask ourselves questions as scientists, right? That's what we do, that's what we're in the business of. When you're doing this SciComm thing, there's just a few questions here you should ask yourself. Who is your intended audience? Because again, you gotta know who your audience is, right? What barriers do you face in that communication process, and can you overcome those? How are you gonna measure your successes? One of the successes of my YouTube video is I have X number of hits. That's not really why I did it, but that's like a measure that you could use, right? And what's the best way to tell your story? Sometimes small, intimate lectures like this are the best way. Sometimes an animated short film is not the best way. You have to figure out what it is that works with your audience, right? Think about, for example, if you speak more than one language, if you're ESL, you're immigrants, a lot of times video works really well because it's kind of universal, even without language in it. So you have to figure out what's the best way, and then how can your SciComm strategy support science through actively engaging with your stakeholders. And thank you for your time. And feel free to ask me questions. And it's so weird. Usually when I speak, I walk around, so I'm trying to stay in the same spot. Oh, no worries. This is a beautiful podium to have.
Hi. This is Ali, graduate student from UMass Lowell. I was thinking, do you believe that scientists really fail to communicate science? And if we failed, what lessons we have learned from that failure? And do you think also, my second question is who are the audience, and we should proactively engage in churches, or we should open the university, what we should do to fill the gap for the failure that we have, if we have.
To bridge the gap, as Hansi and I were saying, yes, thank you for that shameless plug. So first of all, I will say, and I could probably say this about everyone in this room, I don't think any of us ever had a science communication course. As an undergrad, grad, no. It's not something that we're trained to do. For me, I got lucky. I was at a university that had a pilot program with the theater department, and we actually had a SciComm pilot course. Now that is a course that is offered at that university, but that was like a one-off. We didn't even think we'd have funding to do it. So we have to realize, number one, we're not trained to do this. It is important, but we don't have the training. So a lot of times we're going to have to go out and find it for ourselves. There's a lot of SciComm tools online now. AGU has a Voices for Science program. Unfortunately, there is also an NSF-funded program for scientists of color that focuses on science communication that got the axe, so that's no longer around. So it's going to be harder to find it, but it's like we have to figure out where those resources are, whether it's just connecting in small informal groups, like just, hey, look at my slide deck. Does this look good? You know, is there too much stuff on the slide? That's a basic SciComm thing that we can do to help each other. And then the second question was about your target audience, right? Target audience. And it was about trying to identify them. Is that what that was?
I was trying to say we have failure in science section and also I consider that failure. If you bring that to failure, what we can do and what we should change, and should we find like specific target or specific group and audience that will be proactively churches, what things like we can do to figure out that for the future what doesn't moving forward.
I think the main lesson we should learn as scientists, whether we're bench scientists, social scientists, earth and space scientists, we're not perfect, nobody is. We are fallible, humans are fallible, it's by design. That's why we have so many failures in things that we design, because we are fallible and anything we design will be too. But I hate to quote Will Smith after what happened on that stage, but he has a video out, and it's basically about the concept of failing forward, learning from your failures. There's also, I think, a Chinese proverb that a cousin of mine told me. It's like you get knocked down 7 times, you get up 8. So you have to keep plugging away. But we also have to be very self-aware. We have to be like, yeah, this messed up. I'm going to do better next time. You can learn more from your failures than your successes. I can definitely attest to that. Does that help answer? Did I answer it? Good.
Great. Thank you. Thank you, Paula. I do like the idea of an animation. I've always thought it'd be fun to try to animate what actually CSM is, just even for our own sake. It'd be kind of fun, yeah. Yeah, I'm not sure how we do it. Okay, so then our final speaker in this session is Michael Barton. Michael Barton is a complex systems scientist in social change at Arizona State University. He's also the executive in social change at Arizona State University. He's also the executive director of the Open Modeling Foundation, a global consortium of organizations to promote standards and best practices in computational modeling across the social and natural sciences. Michael's research centers around long-term human ecology, landscape dynamics, and the multidimensional interactions between social and biophysical systems, integrating computational modeling, geospatial technologies, and data science with geoarchaeological field studies. So Michael, welcome. Well, there's a pointer if you
advance. I don't think it'll advance because it's on Zoom, so it's okay.
Okay.
We're okay. Where's the pointer? That one? Okay.
The pointer sort of sometimes works.
Oh, it's on. Oh, it's online pointer. Yeah. I can use my mouse.
Okay. Okay.
Yeah. So I want to thank Dave and the leadership of CESM for inviting me here today. It's good to be back. It's a real honor to talk to you all, especially at this 30th anniversary here. I do want to echo something Paula said, and that is no collaboration or communication between the people talking this morning, no prompting from Dave, and all of us ended up talking about different dimensions of how we need to bridge a perceived gap between the kind of climate science that all of us in this room do and the human systems we all live in. And so I'm going to continue with that theme today. I do have to say that CESM is a success story, a scientific success story, starting out actually more than 30 years ago in a lot of the work. It was a computer tool for a few nerdy scientists, and now it's grown from just being a model of the atmosphere to an Earth system model, informing, as we've heard already today, a wide range of different kinds of global policy and global action. It started out as an atmosphere model. How and why did it evolve to an Earth system model? Well, it was because people doing this recognized that the dynamics, atmospheric dynamics, are influenced in a lot of important ways by interactions and feedbacks with other components of Earth's critical zone. Oceans, land, sea ice, a lot of different things. And we've heard about that already. We'll hear more about it this week. But how many here are confident that we fully understand all the Earth systems and we're modeling it? I don't see any hands. We've been studying atmospheric circulation for over a couple centuries, and we still don't understand all the processes, and we either can't model or choose not to model everything that we do know. And this is the case also for the physics of oceans and thermal properties, its biogeochemistry, and the land. But in spite of all this, right, I think everyone would agree that the kind of modeling that's done with CESM has proven extraordinarily useful for understanding past, present, and future of many different aspects of the Earth's critical zone. And of course, in addition to making a lot of important scientific contributions to understanding the atmosphere and its dynamics, it's demonstrated a lot of other things, like the impacts of of greenhouse gases, right, on current and future climate, assessing the impacts of anthropogenic climate change on food production, urban health, urban heat, environment, infrastructure, things we've already heard about in a couple of the talks this morning. And like the atmosphere, oceans, land, and ice, there are important feedbacks between human society, human systems, and all the other components of Earth systems. But these are not modeled in CESM or any other Earth system model today. So I need to remind you all, right, that the Earth system is a coupled natural and human system. That's the one we live in today, right? And I'll put out, in addition to the Earth system modeling, CESM modeling, there's some factoids. I love little factoids sometimes. This is one of my favorite web comics, XKCD. If you're nerdy and you don't know XKCD, you should look it up. So the mass of all of us and our domestic animals is greater than all terrestrial vertebrates combined, right? And our mass and our agrobiomass, over the 3 billion tons, is more than all the vertebrates on land and the sea. And then the stuff that we've made and used, all human mass, exceeds all of the planet's biomass. And then the energy that we're producing and using now is coming close to being the same as the total planetary net primary productivity, right? Almost half of the habitable land is in crops or pasture for our food. Over 30% of all forests have been cleared in the Holocene, and there's a bunch of forests that are still there that were cleared and have grown back. Our coastlines are engineered. Over 70% of fresh water is used for our food production. There's more nitrogen cycled by human activity than non-human processes, and more sediment transported by human processes and than non-human processes, right? So if we accept CESM simulation results, all this work that's been done, if we accept that global scientific data of the impact of over 8 billion of us on the atmosphere, land, and oceans, if we accept the data that people are significantly impacted by climate, that we are affected by that, and that our decisions and actions respond in many different ways to changes in the environment, we have to acknowledge that the way they are now, our system models are missing a critical component, just like they could be missing the oceans or the land, right? And the simulations that we do, no matter how important they are and how valuable they are are less reliable and useful than they could be otherwise. So how do we begin to bridge this gap between the missing human systems in our Earth system models? There's a project that I've been a part of that's been working with NCAR, Louisiana State, and Duke University over the last couple of years, generating actionable research to investigate combined climate intervention strategies for stakeholder use. And the main part of this, headed by Peter Lawrence here at NCAR, has been trying to use CESM to model environmental and social impacts, potential impacts of different kinds of climate intervention strategies. So everything from different kinds of decarbonization to solar radiation management. So what's that going to do to the planet? And I think Peter's going to talk about some of that this afternoon, some of this work. Our role at ASU, the main part of our role, has been to try and develop a prototype modeling environment to bridge this gap for simulating interactions between the biophysical systems and human society for climate interventions. Basically trying to come up with a proof of concept for a new kind of modeling component that could be coupled into CESM and coupled with its biophysical components, right? And so our project focuses on climate interventions. That's what the funding was for. But our broader vision has been to try and develop components that are potentially flexible enough to simulate other aspects of human systems that are relevant to Earth systems, right? And so what we want to do is try to come up with this platform where you could carry out experiments on the potential and consequences of feedbacks between climate impacts, right, including the impacts of climate interventions, and human systems decisions and actions, including climate intervention policies, so we can simulate those and model them in ways that you can't do now. Right? So how many here believe that in the near future, climate intervention strategies, geoengineering is going to be done in this nicely unified world, scientifically guided for optimum human benefit, right? Yeah, neither do I. But this is the way that Earth system modeling is done today. And this can be useful, right? So this is useful to get an ideal kind of outcome, right? But it's imperative to also understand the consequences of climate intervention policy in a more realistic, non-unified world in which we live, right? So what we've been trying to do in this project, Societal Dynamics Model for Climate Interventions, is to come up with a platform that recognizes that climate intervention policies and strategies will be driven by policies at national or supranational levels, responding to significant climate-driven impacts on regional populations, not global temperature averages, right, and sociopolitical conditions. So it lets us try to represent, at least in a simple, in a beginning way, diverse geopolitical actors in different societal scales, right, in different geographic locations that experience societally relevant impacts of climate change differently and that have different kinds of goals and capacities for action. So how are we going to do this? What we've tried to start to do is create a gridded multi-agent formalism with this kind of a model that could interface with CESM inputs and outputs more easily and more flexibly, because this is the kind of formalism that CESM uses, right? So we have grid cells, groups of grid cells that can represent human systems at multiple scales, from cities all the way up to nations and economic blocks. A cell, just like in the land model, can contain subdivisions representing agents at finer spatial scales. Uh-oh. There we go. Sometimes it doesn't advance. This kind of modeling representation lets us represent social actors, either all the way from individuals to groups, right, as heterogeneous agents with different histories, biases, contexts, relationships to other agents. And this allows these different agents, grid cells, groups of grid cells, right, to implement algorithms to respond to conditions from simulated biophysical and social worlds, just like CESM grid cells do in terms of independently activating algorithms to represent thermal conditions in adjacent cells and things like that. Because grid cells, agents, right, are in different geographic space, they can experience geographically different simulated conditions. But they can also do some things different than CESM normal grid cells in that they can also interact with other agents, grid cells, in other parts of the simulated world, not just adjacent ones. So teleconnections, you can think of that. This kind of formalism lets us try to simulate potential impacts of climate intervention strategies in this more realistic social world, where climate intervention policies are carried out by different geopolitical agents, each with different agendas, and they may be working together, or they may be working against each other, or working independently. Decisions of each of these agents on climate interventions can be influenced by unique, different combinations, right, of the simulated biophysical conditions that they experience, climate impacts, right, as well as actions of other agents. And their choices can also potentially, maybe or may not be influenced by CSM simulations, scientific guidance on what may happen if they take these choices. So how we're thinking about doing this, and we've done kind of initial work on this, is that the modeling will be able to connect with CESM through loose coupling so that CESM has starts and stops the simulation at regular intervals, like annual intervals. During the simulation pause, each agent can read and parse simulated conditions from the biophysical world that comes out of CESM, from CESM output files, and then decide on a climate intervention action, or nothing, do nothing. Right? And then this platform aggregates those different decisions together into a forcing file that goes back in and alters the parameters of CESM on a restart, and do this on an annual basis. So here's a little schematic to give you a sense of how this works. What we've done now is it's coded in Python. It's a modular architecture, so it's very flexible. We have this loose coupling with CESM using netcdf files for input and output. We're designing this with CESM in mind as a way to couple it with this, but our goal is to make it flexible enough that it could be used with any other Earth system model that can be stopped and restarted and used as netcdf or some other kind of file for this kind of I/O and coupling. We've also been exploring the potential of using this with Earth system modeling emulators, and you can hear more about that. I think on Wednesday there's a paper on that coming up. So this is just another schematic of what each geopolitical agent does, and this is a group of cells and to be convenient to work with CESM, either with the resolution of CAM, the atmosphere model, or the land model. That corresponds to a geopolitical entity like a nation state. So if you can imagine the grid cells that are equivalent to, we've got Russia there, or Brazil, or North America, right? So each of those agents will parse CESM output, right, for the corresponding cells. Right? And then it will also parse information about other geopolitical agents, what they're doing, come up with a decision or action, and then these is combined into a forcing file. To get started with this is a big job, right? So we have to start somewhere. We're focusing on solar radiation management, specifically stratospheric atmosphere injection, for a couple of real pragmatic reasons, right? One is that an SAI forcing approach is already worked out. So these have already been worked out, and a Python controller scripts have been worked out for the ARISE simulation. So they're already something to work with. And this SAI, if it's implemented, can have relatively near-term impact as opposed to growing forests or something, which is a longer-term impact, with the potential for benefits and risks in the relatively medium term, and that they can vary by place. So something that's good for one group may not be so good someplace else, and vice versa. So there's these differences. And so it makes simulating SAI in this more realistic social simulation especially useful. We're also looking at, for an impact, we're just starting with one impact and using extreme heat. Again, this is something that's likely to have growing impacts in the future, and something that can be affected by stratospheric, atmospheric aerosol injection. Right? And so right now, rather than just take temperature, we're interested in extreme heat that could actually have impacts on human society and move the policy needle. And so we're using an index developed by Jenny Vanos, and it can be calculated from CESM input. And she has like 2 different kinds of indices. One is livability, and this is the ability to actually do stuff outside, so it has economic impact and things like that. And then survivability, and that's the risk of dying from heat stroke, things like that. We're trying to, we've combined those into a single impact matrix. You can kind of see here. And the idea is it pulls in, we can calculate this from 3 different outputs from the atmosphere model, and then we can calculate the daily heat stress, aggregate it for a year, and then compare it to a reference, a mid-20th century reference amount, and then weight it by population to find out what the impact is per country. This would actually go into the policy decisions at this point. And what are the decisions? Well, there's a lot of different ways of simulating human decisions that people have worked on for a long time. Right now, just to get started, we're doing a simple kind of deterministic probability of a decision. So we have information you can see up there. I'm not going to bore you with the math right now. You can look at it later if you want. But the probability of investing in a particular climate impact. We've thought about making that more sophisticated by taking a Bayesian approach, where each kind of information will update an actor's decision making and increase or decrease the probability of investing in different climate intervention strategies. And then kind of further out there, but it seems important in the discussion we've already had this morning, is thinking about large language model impersonation, that's AI, and with the idea that contextualize and prompt this large language model to impersonate a different geopolitical actor, a different country. And so you could give a prompt like this and do it. We've done a little bit of experimentation with that. So here's just a little video to kind of show you a little bit how this sort of works. I have a couple of these. And on the left, you can see this is the effect of picking a particular SAI injection point and what its impact is on different places in the world over a 10-year interval, right? On the left, I guess the left up there, say it. And on the right, it's what this would look like if different actors chose different injection points. Just to point out that there's different effects depending on what kind of choices get made on this. And then this is a quick simulation of, or a video of a simulation where we've just created 6 different likely actors, large countries or country blocks, and then they perceive heat impact, and that gives them a probability of wanting to invest in SAI. And you can see how this changes as the colors change on the on the outlines of the countries here. And you can also see the actual heat impact changing in the world there. So this is what the actors experience. Right? So the plan, right, would be to include other extreme impacts beyond heat, extreme drought, agricultural failure, extreme storms, floods, wildfires, sea level rise, things that likely would affect policy in different ways. And then, of course, have other climate intervention strategies. This whole project was to try and simulate the impact of up to 8 different strategies, everything from reforestation to SAI and some things in between, right? But in the future, a platform like this one perhaps could alter other CESM parameters using the same approach to change things like greenhouse gas emissions in response to societal decisions. So the idea is to kind of create this framework that could be used for a variety of different kinds of things in Earth system modeling. So I think it's in the world that we live in today, especially right now, it's more than ever important to try to represent Earth system models, human systems and Earth system models. You know, the changes that we are making to Earth systems are generating many, many different kinds of extreme events, ones that are hard to predict, and these have significant impacts to human survival and well-being, things that actually may change the policy needle in some ways. At the moment, human society globally is getting less unified instead of more unified, and with the potential for, I think, significant cascades of societal transformation, to be a little bit euphemistic about it. And there's a growing potential for independent climate intervention actions by global actors that want to seek relief from extreme impacts in some way or score political points locally. So these things are all, I think, happening, which means we need to at least try to understand what the potential is in this looking forward. And so we need to recognize this is a serious issue. So a number of people have written about this recently. And we need I think, a concerted, collaborative effort to try and develop these kinds of representations of human system dynamics within Earth system models. And so this is, I think it's important, especially in a collaborative community like this. Right? ASU has been doing this as part of this project, right? We can't do this alone. This is obviously not something for a single university or anything else. And we're at the end of our NSF funding for this, right? So we've gone as far as we can go with the current funding, and in spite of how important it is, the potential for getting new resources to continue any of this kind of climate work are diminishing rapidly. We all know that, right? But even if they weren't, right, in a different world, even with significant funds, right, trying to create this kind of a prototype to simulate more climate intervention strategies and other human system dynamics inherently will take a large-scale collaborative effort. Keep in mind, CESM3 that we heard about this morning builds on like 6 decades of developing global climate models, right? Global circulation models. So we know that these things take time and effort and benefit from collaboration. There are a lot of other groups besides what we're doing at ASU to think about modeling this kind of things, that have thought about how to model the interaction between human systems and Earth systems, right? So this is going on now. There's a lot of stuff out there. If there was a framework for more collaboration and coordination together, a lot of the work that's ongoing right now could accomplish a lot. The kind of working groups that are here at CESM are recognized umbrellas for this kind of collaborative research and for sharing knowledge. So they've been vitally important to the development of CESM as the world's premier Earth system model. There was a Societal Dimensions Working Group that was created a decade and a half ago. Unfortunately, it dissolved under conditions similar to what we face now, but they're not quite as bad. And this working group can't be revived as it was before. I mean, that was 2011. That's a long time ago. But we still need some kind of a new working group framework, I think, within the Earth system modeling community to support the kind of collaborative science that's needed to develop a human systems component, and bridge this gap between human systems and Earth systems. And so, as I would say, like I said, I think the planet's most sophisticated Earth systems model, and perhaps the largest collaborative group in developing this system model. And I want to challenge you all to maybe try to lead the way in organizing this kind of framework that can help bridge this gap in human systems and Earth system modeling. So thank you very much. Thanks to all the people that collaborated with this, and I have a reference section if people want to see the slides later. Thanks.
Questions at the end?
Thanks for an interesting and provocative talk. We struggle with communicating sometimes the uncertainty in the results of our physical models. There are huge financial incentives for predicting the evolution of human systems, and it seems to be very difficult to do, even given those incentives. So I'm wondering if, in the fusion of these two systems, if you foresee an explosion of the uncertainty of future scenarios, and then how do we communicate that? Often we like to give error bars, Are you thinking more that you talk about representative storylines? How do you communicate that huge space?
So the first answer is yes. I would expect an explosion in the amount of uncertainty and things like that. Having done a much smaller scale coupling of human systems and biophysical systems, that is indeed what happens. Communicating uncertainty to others, especially outside the scientific community, is difficult. I mean, this is reality, right? I think one of the things that we need to do is be honest, and this includes for the kind of climate modeling scenarios that we do now, the storylines, you say, I mean, that's one way to do it, is to point out that we're not predicting the future of human society. We're not predicting the future of climate on the planet. What we are doing are trying to anticipate potential futures given a series of things that we do, of incomplete modeling that would help give us guides. So I think I tend to try and really try to talk about this kind of work as carrying out experiments on potential outcomes given a certain set of conditions, rather than say, this is what's going to happen, and you've got, be prepared for it. So, but this is a difficult thing, and I think it clearly, as the other speakers this morning have pointed out, it's difficult for the kind of Earth system models that we're producing right now is to communicate these things. I think adding humans to it make it more complicated, but also potentially more appealing and maybe more useful to more people on this. We have to acknowledge the limitations.
Thank you. I had basically the same question, but now I want to be more specific. So we've been prescribing human system by designing emission scenarios.
Right.
And that's basically a simplified way to quantify the uncertainty associated with human activities. And I guess my question is, how do you envision in the future, what factors in the human system are important to quantify the uncertainties?
I mean, that's a really important question. And it echoes the same questions we wrestle with all the time in biophysical models. We don't represent every single thing that's going on. We make choices, and sometimes we make the wrong choice, but we try to make useful choices on these things. And so for the kind of little prototype we're doing now, I mean, horribly simplified. We're just talking about one set of decisions, one kind of impact, and one kind of decision. But I think that's still useful. And so I think the important thing is to move beyond simply thinking of people as a parameter to input into these models, but as to begin to represent the feedbacks and interactions with people, even if we do it in a simplified and unrealistic way. It adds, I think, much more value to the models that we do. So thanks.
So my comment is similar to the first two ones. So if you move the scenario uncertainty into the model, it's the IPCC projection will be just one big distribution, and you take human agency out of that, and it'll be difficult to communicate what good and bad is. So taking human agency out, I think, is a very dangerous thing to do.
I'm not quite, I understand your question.
Because
Sorry.
you're moving the uncertainty associated with human activities into the model. And if you do an IPCC projection with this comprehensive human natural systems model, into multiple scenarios, you'll just get one wide spread. And it'll not be clear what we need to do because it's a complex model.
I think we need to think about it maybe in a slightly different way. And so, again, we're not predicting the future of human society. The question is to say, what would happen under the following circumstances? And so we end up specifying the boundary conditions, just like we do in physical models. We specify boundary conditions for human systems. We can't model the individual behavior of 8 million people any more than we can model the behavior of fish in the ocean or the molecules of nitrogen in the atmosphere. What we can do is try to say, these are, as you were asking here, these are important dimensions that are worth asking. What would happen, what might happen if these dimensions were set in these ways? And so think about it in terms of setting up experiments than trying to represent the great uncertainty in knowing what global human society is going to be in the next decade, much less several decades.
Yeah, thank you, Michael, for for a great, inspiring and interesting talk, thought-provoking. Group sessions after lunch, and then at, I think it's around 4:30, 5 o'clock, we have the poster session and reception. So look forward to seeing you all there. Thanks again to all the speakers for a great session.